referred to red dots, the actual data blue dots, and the best fit obtained from neural network as is the black curve, and all the red curves are referred to uncertainty intervals. So generally there seems to be similarity between the predictive curves and the exact function solution of SEDM. To a large extent, the uncertainty intervals are observed to find the actual value of data and give good coverage, except in initial production period, which leads to a greater mismatch and possibly reduce the accuracy of predicting the initial real times. Even though the cumulative production or estimate ultimate recovery closely matches. Basically, it's same interpretation and for other results as yeah, here it shows better uncertainty coverage for actual data, and here it also shows a mismatch at least initial 12 months. Yeah, so here we can say that we can conclude that Bayesian ODE model is capable of accurately predicting both the downward and upward trends for most of the world and perform better than the standard method SEDM, which is deterministic. However, the forecast phase significantly captured both trends and peaks for some worlds at initial 1 year, which means that the model cannot really predict when there will be a change in production or there is any other activity like workover or so on. One way to improve the study to include Bayesian framework in the concept of physical informed neural network. Here I'm showing an example of physical informed neural network applied to decline curve analysis, which has been introduced by Daniel Busby. The author here has included decline curve analysis as a constraint in neural network, where where the loss function is for training is a weighted sum of the error between the observed and model data, and error between physical and modeled OD or PD equations. As a conclusion, we can say good decision making requires support from data analytics and both mathematical and physical modeling, and the application of physics guided by machine learning holds a large value potential in energy sector.
Thank you, Amin. Taja. We would now like to invite the judges to ask any questions.
Hi, Amin. Very great presentation. Thank you. The questions I have, so for the backend field, the production, is it only 40 months as of now? And then the second question was, the amount of data you used was 305 wells. Have you looked into the possibility of what less data or more data could be on your model for forecasting? Thank you.
Yeah, thank you for the question. So for first question, I mean, we have selected like data that contain at least 24 months of production duration. So at least we can generate like a decline curve models. And for the second one, it's like first the data is like as I showed in my report, it was publicly data set. So I don't have like a lot of access to input variable. So that's why we have just selected around 305 wells 305 watts. But we believe that with more data, we're gonna do more training. We're going to improve. I mean the accuracy of machine learning. And one thing I did mention in my presentation talk is like the accuracy of this workflow depends mainly on the input variable. So here we have selected only like some geometric and fracturing due to the data availability. But we believe that more data like related to maybe to viability or I mean or geological other parameters could also improve the accuracy of the model.
Thank you.
Hello, thank you for your presentation. Yongzan here. My question is that do you need to predetermine a decline curve analysis model? Or does different model have significant impact on your predictions?
Can you please repeat the question? Because I missed the first part.
My question is, you need to predetermine a decline curve analysis model you will use for your training, right?
Yes.
And the different model does different model have some impacts on your predictions or on your model?
Yeah, so here it's like basically what I have done is like the first question we have asked is which model should we use for decline curve models. So as I said, many of them can fit data equally, but provide different forecasts. This is why this have to introduce the concept of Bayesian neural ODE. It's like we select here we select like a SEDM. So the main purpose here for SEDM, instead of getting like deterministic, we try to quantify uncertainty, include the concept Bayesian framework of prior and the likelihood and posterior. Likelihood here mostly is like it's embedded between the error between like the deterministic and the loss function of my machine learning. So here it's like I can say that here we didn't really answer the question which model we should use. We instead answer the question, how can we quantify the uncertainty? Uncertainty of the decline curve models.
Oh, okay. Okay, but yeah, my second question is kind of a follow-up. So because I think you have one data per month, right?
Yeah, it's
so
monthly.
I think yeah, to me the resolution in the time scale is kind of low. So I think this resolution will lose some details or the production characteristics.
That's correct.
Yeah. So do you have any comments on that?
Yeah.
What if the data is very in the time scale is very high? So we have probably one data per day. Probably the decline curve does not have a good fit to the field data, right?
That's very interesting question. So here again, it's due to the data availability. That's why we have used only monthly time step. But I think it would be very useful to explore this framework in daily data, daily production.
Okay, thank you.
Thank you.
Thank you for an interesting paper. So the question I have for you is, suppose if you had considered only half the data set and tried to use that for your extrapolation, could you then see what the actual production for the remaining half was, as opposed to what you would expect? I mean, what you would project? And can you make analysis like that? And how might it help you?
It's like mostly, if I understand well the question, it's like instead of using like 80%, 20%, I'm gonna use like 50%.
Yeah.
Yeah.
You have a history of data for 40 months. So if you use only the first 20 months data and use that data, to come up and then project it to 40 months to see how your projections match with the actual data for between the 20 months and and the 40 months.
Yeah, that's very like interesting way to improve this study, how to explore it. Yeah. So basically here it's like mostly it's like we use 80% for training and 20% for testing, and just to try to predict like a surrogate or proxy model, a surrogate or proxy model of DCA parameters based on basically on because first with 80% of the testing data, training data, it's like we generate a profile, DCA profile for the entire period. But I think, yeah, it's a very interesting question. We should at least generate at least for 50% instead of using the entire production period.
Well, you may also consider that, you know, like you said, if you use 50% for training and then 50% for testing, if you can increase that to 75% for testing and, you know, 25% for, I mean, 75% for training and 25% for training, and see if your reliability improves or in what direction it changes.
Correct, yes.
Because many times we will have very limited data. You know, early in the life of a well, we will not really have a 20 months data. I mean, you know, 40 months data. We will only have maybe 5 months data or maybe 10 months data, and so we have to use it.
That's correct. Yes.
Okay. Thank you for
Thank you
interesting
very much
presentation.
for the constructive feedback.
Any further questions from the judges? Okay, so with that silence, I will take it as no more questions. So we will move on to the next presentation. So our next presentation, we now move on to Prakash Paswani, winner of the Eastern North America Paper Contest.
Greetings. Thank you for tuning in to my student paper contest presentation. I'm Prakash Paswani. I'm a recent PhD graduate from the Pennsylvania State University, member of the SPE Eastern North America region. Today, I will be presenting a part of my PhD research, and the title of my talk is Impact of Variability on Capillary Phase Trapping using Pore Network Modeling. Let me start with some general background. The topic of energy transition is of great interest in the oil and gas industry and across energy industries at large. Here are some key headlines from the industry just in the past year, published across SPE platforms. Houston, the energy capital, urged to lead the energy transition. How major oil and gas companies are preparing for energy transition. How different energy forms should coexist to meet the grand challenge of energy transition. Transitioning to a greener energy and the role of digital technologies in achieving a zero carbon future. To achieve a greener energy transition and for accomplishing net zero carbon future, all technologies that can help minimize greenhouse gas emissions are being considered. Carbon capture is one such promising technology for minimizing greenhouse gases. Carbon storage in underground formations through capillary trapping is one such mechanism that will be explored in this presentation. Let us understand capillary trapping. The video on the left shows the main imbibition process. The green is the non-wetting phase like CO2 that is occupying the majority of the pore space. Here the clear background shows the wetting phase like water, which is displacing the CO2 phase. Pore scale processes like snap-off, bypassing flow, layer flow, and piston-like advance take place during such displacement processes. At the end of the main imbibition process, you can see that some of the phase is not able to be removed and remains completely trapped, as is shown here. This is the residual non-wetting phase saturation, which marks the no-flow boundary. This is the stage of capillary trapped CO2 in the subsurface. Now that we understand phase trapping, let us understand wettability. Wettability is the property of the solid. It is described as the preference for one fluid in the presence of another fluid. For example, preference for water in the presence of CO2 as shown on the picture on the right. Wettability results from the balance of interfacial forces as is shown in the figure. Wettability affects how fluids distribute in the pore space and can therefore affect phase trapping. It is therefore an important rock property for CO2 storage. Here are some key developments from the literature in the space of wettability and phase trapping. Amit conducted spontaneous flow tests to quantify wettability through Amit indices in 1959. Land proposed a trapping model for saturation based on initial phase saturation in 1968. Next, Salatiel in 1973 proposed the mixed wet term for the first time. Moreau in 1975 conducted experiments to understand the phenomenon of contact angle hysteresis. Lenormand and Zarcon performed micromodel experiments to understand the physics of fluid displacement. Chatzes et al. In 1983 conducted experiments to study the effect of pore structure on phase trapping. Jadunandan and Moreau in 1995 conducted experiments to understand the nonlinear behavior of phase trapping with wettability. Spiteri et al. Proposed a new model for phase trapping for different wettability conditions by using pore network modeling. Herring et al. Proposed the trends of phase connectivity during multi-phase flow. Perswani et al. More recently analyzed the trends of residual phase connectivity using pore network modeling. In this presentation, we build on these works to answer the following research questions. How does wettability affect phase trapping in a porous medium? Can simple functions model and predict phase trapping? What is phase connectivity and how does it impact phase trapping? To study the trapping trends, we conduct pore scale numerical simulations using pore network modeling. For this, we first extract the internal structure of the porous medium using X-ray CT and extract its corresponding pore network architecture. Different flow mechanisms can be simulated using this technique, and we perform different flow sequences such as CO2 injection and water injection to arrive at the trapping trends. These simulations are performed for different wettability cases to study the effect of wettability on phase trapping. Using pore network simulations is advantageous in achieving strict controls on flow conditions, such as the pore structure of the medium or the wettability of the medium. Here are the results for phase trapping for different wettability cases. The plot on the right shows the fraction of the trapped phase or the residual phase saturation on the y-axis, and it is plotted as a function of the initial phase saturation. The colors represent the different contact angle cases considered. For example, in red shows the case when the phase is non-wetting to the medium, whereas the blue shows the case when the phase is wetting to the medium. Notice that as you increase the initial amount of the phase, you increase the amount of the trapped phase in the medium. As you change contact angles to change the medium's wettability to be more wetting to the medium, you decrease the trapped phase in the medium. This occurs because of pore scale processes like layer flow or piston-like advance by the invading phase that leads to an efficient displacement of the receding phase. Here also notice that a maximum trapping of around 0.5 saturation occurs close to an initial saturation of 0.9 for the intermediate wetting case. Such nonlinear trends, however, may not be found through typical core flooding experiments because such high initial phase saturations may not be reached from experimental conditions. The next set of results are for modeling the trapping trends. First, we consider models from the literature. The plot shows trapping trends for 4 different contact angle cases, from very non-wetting shown by the blue color to very wetting shown by the purple color. The symbols are the data points from the PNM, while the dashed lines are the model fits. This particular plot, I'm discussing the LANS model, and the equation for the LANS model is shown on the left. This plot summarizes the goodness measure of the fits for all wettability cases. Notice that although the LANS model is simple with a single parameter is C, it does not perform well when the phase is wetting to the medium. The second model that I will be discussing is the Spiteri model, which was an improved model. It is a quadratic model and it performs well over the entire range of wettability, but does not collapse to the LANS model. And looking at the fit, it also seems that this model can still see further improvements. Based on these deficiencies, we developed a new model. This is a simple generalization of the previously known LANS model. Notice that the model performs excellently well across all wettability conditions, and also that the model easily collapses to the LANS model as parameters A and C approach a value of 1. So far, we have only considered trapping from the point of view of phase saturation. Let us understand what is phase connectivity and how does it impact phase trapping. Phase connectivity is estimated mathematically from the Euler characteristic, which is defined as the number of objects minus the number of connections in that phase. The schematic here uses a ball and stick representation and is showing increasing connectivity from the left to the right. Notice that the number of objects in the schematic are the same, but as the number of connections increases, the phase is becoming more connected. The Euler number becomes increasingly negative at the higher phase connectivity. Here, the Euler number changes from plus 10, which is the most disconnected state, to a value of minus 10, which is the most connected state. We use these two endpoints states to normalize the Euler characteristic and define phase connectivity such that it scales from 0 to 1. Here I am showing how phase connectivity evolves with phase saturation. The y-axis shows the phase connectivity which scales from 0 to 1, and the x-axis shows the phase saturation. A value of high phase connectivity appears at a high value of phase saturation. The arrow marks the direction of flow. The red open circles are the starting point of a particular saturation connectivity path, while the black open circles are the residual points, or also known as the terminating points of that particular saturation path. When the phase is non-wetting to the medium, we see that there is a gradual decrease in phase connectivity as the saturation of that phase decreases. When the phase is wetting to the medium, however, we see that there is a significant shift in the phase connectivity phase saturation paths, and we observe nonlinear trends which were not observed for the non-wetting case. This is because when you have a highly connected phase and when the phase is wetting to the medium, its displacement is much more efficient and you are able to achieve much lower values of phase saturation, which gives rises to very nonlinear phase connectivity phase saturation trends. In this plot, I am showing the combined residual loci in the connectivity saturation space for all contact angles considered. The identification of the residual locus is critical for reservoir modeling purposes because it helps identify the true limiting condition in the phase connectivity phase saturation space, meaning that the relative permeability at this locus is 0. Here, the dependence of residual condition on wettability can be easily visualized. When the phase is non-wetting to the medium, which is given by the red colors, you see that the locus is fairly constant. Whereas when the phase is wetting to the medium, which is given by the blue colors, you see that the closed loop trends in residual phase connectivity are found. This shows that the locus depends strongly not just on the initial starting condition of phase saturation, but it also depends quite strongly on the wettability of the medium. In this plot, I'm showing a simple function that helps capture the trends of phase connectivity for different wettability cases. Here, the function of the residual phase connectivity is developed against its initial phase connectivity, as was done previously for the residual saturation. The symbols once again show the P&M data point, while the fits are shown by the dashed lines. A simple quadratic function, such as the one that is shown here, helps describe the residual phase connectivity trends across all wettability cases. The goodness measure of these fits is shown on the right. X0 on the function represents a constraint on the model, whereas A and B are the tuning parameters. This is for the first time that residual trends are modeled in a simple fashion, as is done here. Here I am summarizing all residual trends for different wettability conditions. The left plot is for residual phase saturations, while the plot on the right is for residual phase connectivity. The corresponding functions that have been developed in this research to predict these trends are also shown on this slide. Simple functions such as these can effectively capture all trapping trends for all wettability cases considered here. With the combination of these two functions, the residual locus for all wetting conditions can be described effectively. To conclude, we see that the amount of the trapped phase depends strongly on the wettability of the medium. We find that mechanisms of layer flow and piston-like advance by the invading phase can significantly reduce trapping if the phase is wetting to the medium. Maximum trapping is found near initial saturations of close to 0.9 when the trapping phase is intermediate wetting to the porous medium, and the maximum trapped phase saturation is found to be close to 0.5. We also find that simple functions can help predict trapping trends across all wettability cases. We see that residual locus, which is bounded by the residual phase saturation and residual phase connectivity, marks the true limiting conditions to flow, and that wettability impacts this residual locus quite significantly. Overall, this investigation uses numerical methods such as pore network modeling to show the impact of wettability on residual trapping of a phase, which can be critical for processes like CO2 storage. I would like to thank the following institutions for providing funding support for my research. And I would also like to thank my dissertation advisors at Penn State, Dr. Russell T. Johns and Dr. Zulema T. Karpin, for their time and advice throughout my research project. With that, I would like to thank you for your time and attention, and I would be happy to answer any questions. You can also reach out to me at the email listed on this slide if you would like to discuss my research further.
Thank you very much for your presentation, Prakash. We would now like to invite the judges to ask any questions.
Thank you, Prakash, for your nice presentation. Very clear, very good presentation. I really enjoy it. Yongzhan here. My first question is, what's your pore size distribution of your numerical model? Have you tried different pore size distributions?
Thank you, Yongzhan, for your comment and your question. So the pore size distribution was actually extracted from a real Benthamer sandstone, and the number of pores were close to 40,000. and the number of throats were close to 25,000. I think the number of pores were close to 25,000 and the number of throats were close to 40,000. So with an approximate coordination number of 5. And to your second part of your question, we did consider other pore structures, but I have not shown in this particular research. So for this paper, we only considered the pore structure from Bentheimer sandstone.
Okay, thank you.
Hi, Prakash, excellent presentation. I have 2 questions for you. So the first question I have is, what would you expect is the percentage contribution of capillary trapping to the storage of CO2? And the second question that I have is, during your simulations, the non-wetting phase, which fluid was used? What are the properties? What was the non-wetting phase? Thank you.
Thank you, Rita, for the questions. So the first question, the percentage of capillary trapping that we see from our investigation is if we have an initial saturation of close to 0.9, 50% of that phase will be trapped through capillary trapping at intermediate wetting conditions. Of course, it is a function of the wettability. And that's why the impact of wettability is quite significant, because if you reduce the wettability of the phase to be wetting, at the same initial saturation conditions, you can reduce the effect of trapping quite significantly. To the second part of your question, we used for our numerical simulations, pore network modeling works as an architecture where a stepwise process happens. So a step change in saturation occurs with a step change in capillary pressure. And as you increase that capillary pressures, your invading phase or receding phase are able to move through the pore space. In terms of the properties, we use the same viscosity ratio for the 2 fluids. And in terms of wettability, there was not necessarily truly a non-wetting phase, because we were exploring wettability at different contact angles. Thank you.
Hey, Prakash, very nice presentation. I have 2 questions. So the first one is in slide 9, if we take one constant oil, initial oil or initial saturation, you see that the intermediate phase has the highest residual saturation. So what could be the explanation of this phenomenon?
So thank you for that question, Miral. And this is something that was quite interesting to note from this research. And one of the reasons why we are able to see that case is because we are hitting much higher initial phase saturations, which may not be typically happening from experiments. Because we don't achieve such high capillary pressures through typical core flooding experiments to establish our initial conditions. And this is something that is still an ongoing investigation. And we are also reporting on these findings of our residual trends, which are not necessarily seen from experiments for the reasons that I mentioned. And it could be one of the reasons that we think that why intermediate wetting is doing well is because how it is typically reported in the literature is that wettability is reported as Amit indices or Amit-Harvey indices, which are extracted from a full core flood experiment, which could be an average measure of wettability for that core. And here we are actually explicitly giving wettability measure through contact angles. So we have a much more defined or refined interpretation of what wettability is in the pore space. So yeah, that would be my answer. Thank you.
And my second question is for the trapping models that you're proposing here. Are there any rules of thumb of the values of those tuning parameters to use for, say, a sandstone versus a carbonate, and if there's any physics-based parameter that's related to those that can be
Yes, thank you for that question as well. So we in the paper that I have and that I'm writing on this, I mean, I didn't have it on the presentation. But what we do is the fitting parameters that we have, for example, the residual saturation versus the initial phase saturation. There are 3 fitting parameters, A, B, and C, and those can inherently be functions of the wettability or the pore structure of the medium. So currently we have the pore structure constant, so those can be explicitly functions of the wettability of the medium. Once you have them characterized as a function of wettability, you can take your rock and you can define its wettability and then, or measure its wettability or average wettability, and you can use those functions to predict what your residual saturation could be at some initial conditions. Thank you.
So Prakash, I want to congratulate you for your excellent presentation, very clear exposition. My questions are that if we, think about going in, you talked about carbon capture. So if we consider a situation of a CO2 storage in a aquifer, saline aquifer, then what would you be telling people that how much of the CO2 that you injected is going to be lost as discontinuous phase, that will not be produced back from the experiment and modeling work that you have done? What kind of guidance can we receive?
So that's an excellent question, Anil, and thank you for your comment on my presentation. This is something still very fundamental research in terms of carbon storage in aquifers, and I understand that the industry is in the method or in the process of scaling that up. And what my research poses is an important investigation and characterization that needs to be carried out fundamentally to be able to exactly answer the question that you're posing. How much of that CO2 could be lost? How much of that CO2 could be stored, and so forth? And what we are seeing is that impact of pore structure, where capillary trapping exists, and course, together with that, the impact of wettability, how that phase is able to recede, are extremely critical rock fluid properties that needs to be investigated carefully when you're considering such processes, especially you want to scale that up. We also see from other experiments in our lab that aquifers or even simple barrier rocks where we inject CO2 at supercritical conditions may not necessarily be non-wetting to the medium. And we find that its average wettability could be close to 80 degrees, which is an intermediate wetting case. And if this were to be, then we have to investigate how much of that trapping could occur, and consequently, how can we scale that process to make such recommendations for the industry.
So can we hope for some answers in the future?
I think we should, yes, we definitely should, but I think we should also investigate and put more funding in terms of research and characterize the media more effectively at reservoir conditions to be able to certainly answer those questions.
Thank you.
Thank you, Anil.
Prakash, excellent presentation. Thank you so much for that. I see promising results in here, but would you kindly elaborate on what it could be the limitation in such a study? Thank you.
So thank you, Nuf, for the comments and the question. One of the limitations is that, as I mentioned, experiments are not able to reach such high conditions. We may need methods like higher forced injection to be able to achieve such high initial saturation. So we need to first corroborate what we are finding from numerical simulations here from experiments. One of the other limitations, as I answered to Anil's question, is that we need more research and we need to expand it to other pore structures, other rock fluid properties to ensure that we are able to replicate them, not just experimentally, and then do simulations to help scale that process up. Other limitations I see is just from experiments, achieving high pressure, high temperature conditions can be very difficult. So those challenges need to be overcome to be able to scale the process, I would say.
Thank you. Any further questions from the judges? Okay, before we move on to the next, would the participants like a short break, or are you happy to move on to the next one before the main break?
I'm okay to go on to the next one, then break. This is
Okay.
your plan.
Yeah, same here.
Thank you so much. Okay, sure. We will move on to the next one. Okay, so thank you, Prakash, and thank you, judges, for the question and answer session. So we now move on to Deborah Matogi, the winner of the Gulf Coast North America student paper contest.
Hello everyone, thank you for being here. My name is Deborah Martugi, and I recently completed my PhD from Texas A&M University. And today, I would like to present my work for the SPE International Student Paper Contest. This work is titled Microscale Techniques Characterize Elastic and Fracture Properties from Rock Cuttings and Rock Fragments. So what we usually do to get rock mechanical properties is to perform well logging and get core samples. The problem with well logging is that they are costly to perform, and that the data resolution we get depends on the frequency we use. In addition, we typically need to get core samples to calibrate these well logs. Obtaining cores has been known to be expensive and risky. They also increases our downtime. Plus, as we drill into the unconventionals, obtaining cores from the horizontal section of the well has been known to be challenging due to the risk of tool jamming and instability. And this is why only about half of the wells drilled in North America are logged. Meanwhile, previous studies showed that tons of drill cuttings are produced throughout the well, which could be a cost-effective resource and lead to higher resolution data. And this is why in my study, I'm trying to address this one question. Is it possible to get rock mechanical properties from rock cuttings and rock fragments? Conventional methods use these core samples and block samples, and testing on these cores typically runs hours, days, or even months. It's also usually destructive, so we cannot reuse the samples. In my study, however, each test takes about 3 minutes to run, and I can even perform multiple tests to increase the certainties in my analysis. And this is why developing this methodology is very valuable to our industry. So I'm gonna start with elastic properties approximation from rock cuttings using indentation tests. And I'm not the first one to do so. There has been some extensive study performed at the nanoscale level, where at this scale, we can obtain the mechanical properties of faces along the surface of the rock sample. We then need to upscale the results to homogenize these points. Indentation test has also been done at the macroscale level, where at this scale we have a direct access to the bulk mechanical properties. The problem that I saw in most studies done before is that I noticed these jumps, kinks, and discontinuity, and that relates to fracture formation, which should be avoided when we evaluate elastic properties. What I had also seen in previous studies is that most studies only consider rock as isotopic homogeneous material, which is defined by this one Young's modulus E and Poisson's ratio phi. This is not true, however, as shown by the cores here, there is some layering signifying rock anisotropy. So in my study, I consider rock as an anisotropic material with one symmetry along this bedding plane orientation called transverse isotropy. And their mechanical properties is defined by the CIJ matrix, which I will talk about more later. So to get the elastic properties from indentation tests, here's what I do. First, I collect the indentation modulus measured on randomly oriented cuttings. What I mean by randomly is I have no knowledge of the bedding plane orientation since I can't visually see it unless I inspect each cuttings under SEM, which is time consuming. I then use the experimental data as the input to an inverse algorithm or optimization developed based on contact mechanics solution. Once the optimization completes, the output to the inverse problem are the 5 elastic constants for the TI stiffness matrix and also each cutting's orientations. So to collect the input for my analysis, I ran a microindentation test on the rock cuttings. And this is the microindenter that I use, where what it does is just load the sample or poke the sample surface. And throughout the test, this load displacement plot is recorded, where I can then determine the stiffness of the material based on the initial slope of this unloading portion of the curve. I can then relate the stiffness to the indentation modulus using this first equation. Now that I have the experimental results, I need to convert that into the elastic properties. And to do that, I use contact mechanics. The elastic properties that I'm looking for is this CTI stiffness matrix, which is a function of up to 5 elastic constants as shown in this matrix. And each of these constants is defined within this reference coordinate system, where I define the bedding plane orientation. So when I load the sample perpendicular and parallel to bedding, the loading orientation shown in yellow will be aligned to one of these axes. The resulting contact area will be symmetrical as shown by the circle for perpendicular loading and by the ellipse for parallel loading. As a result, there is a direct correlation between the stiffness matrix and the indentation modulus M obtained from the experiment. And M3 is for perpendicular and M1 is for parallel to loading. So for any other loading orientations, there is no such direct correlations, and I need to consider anisotropic contact mechanics. The displacement due to loading is captured by this Green's function, where Wy is in Cartesian coordinate system and H theta is in polar coordinate system. Here again is the reference coordinate system where I define stiffness matrix and also bedding plane orientation. And BKN is where I define the stiffness matrix. This misalignment between the loading plane orientation and also the reference coordinate system is captured by this direction cosine beta k shown here. And this misalignment cause some rotation in the contact area produced, and that's captured by the angle phi. Now the Green's function is rotated by the angle phi, and that's captured by this alpha function. I can then take the inverse of this alpha function to compute indentation modulus. In my case, I know this indentation modulus from the experiments. I don't know the loading orientation or the stiffness matrix. So I actually have to reverse this process, and to do that, I perform optimization. So what the optimization does is simply minimizing the error between the measured modulus from the experiment and the predicted modulus based on the solution I showed in previous slide. Once this error is minimized, the algorithm will provide the best predicted stiffness constants and also each cutting's bedding plane orientations. In my case, I don't know the bedding plane orientation on each cutting, so there's a high likely chance when I load the sample, the loading orientation won't be aligned with the bedding plane orientation showed by the red reference coordinate system here. What I noticed in the initial analysis is that there are some variations in the results as shown on the left here. This then leads to uncertainties which affect the accuracy of C13, C33, and C44 values predicted. So to improve my analysis, I prescribe additional constraints such as the Poisson's ratio and the Thomson parameters constraints. This then resolved the directional issues, but I still noticed some variations. These variations is due to uncertainties in the experimental results, and to address this, I implement Monte Carlo simulation. To run the Monte Carlo simulation, I consider each experimental data point shown by the orange square, along with the error bar shown in green, as a normally distributed PDF function. I then select points randomly from this PDF function as the input to my Monte Carlo simulation. The results that I obtain after the simulation is shown here on the left for Marcellus and here on the right for Permian. The gray lines are pretty much the upper and lower bound result of the optimization. The yellow dashed line is the result when I use the average data point as the input to the optimization. The 5 elastic constants predicted are shown in this table, each for Marcellus and Permian, which I will validate next using a dynamic test. For the dynamic test, I performed ultrasonic pulse velocity tests on a cube sample that's about 30 to 40 times larger than the cuttings used for my indentation study. What I pretty much measure is just the velocity that it takes for the elastic wave to travel through the sample. I then perform the measurement at multiple orientations and get different velocities, which I will then convert into the elastic constants for transversely isotopic material. I then compared the results measured from dynamic test to indentation test. The results measured from the dynamic test is plotted along the horizontal, and the results predicted from the indentation test is plotted along the verticals. These diagonal lines are pretty much a similarity line, so the closer the data points plots to these lines means that the results between the two measurement methods match well. And as you can see, all data points plot pretty close to these lines, which means the results from indentation test compares well to the dynamic test. This then proves that the methodology I developed works to identify anisotropic elastic properties from rock cuttings. And that brought me to the end of the elastic portion. I will now move into fracture toughness approximation. Conventional fracture toughness approximation like 3-point bending, semicircular bending, and short rod require complex sample geometry, pre-notching the sample, and sophisticated test setup. This is why, in my study, I use scratch tester, which requires small sample volume and has high repeatability. I'm not the first one to do so, however. Dr. Akono and Dr. Ohm has developed a methodology to approximate fracture toughness from scratch tests. Their study uses linear elastic fracture mechanics, or simply LEFM, and J-integral methods. These approaches are not able to accurately capture crack initiation and propagation, and this is why in my work I coupled scratch tests with phase field modeling to address these limitations. So again, starting with how I approach this problem. First, I get the input for the analysis from scratch testing. The main inputs I need are the panoramic picture taken after the test as shown here and the force displacement data. Next, I use this information for the analysis. I first use the panoramic picture taken to identify the types of fractures being developed. In this case, I observed tensile and shear fractures. I then derive the analytical solutions to get fracture toughness from each segment. To do so, I use phase field modeling. Once I analyze the segment, I get the output that I need, which are the tensile fracture toughness and the shear fracture toughness. So first, for the input, I collect the data using scratch tests. So this is the scratch tester I use, which basically scratches the sample under increasing load. Throughout the test, all of these parameters are being recorded. In particular, the parameter I'm interested in is this red line, which is the acoustic emission signal. These peaks signify fracture formations. Other than that, I'm also interested in the panoramic picture taken after the test, which helps me identify the fracture developed. Now that I talk about the experiment, I will move into the analysis. The first part of the analysis is to identify the fracture types, and I did that using these panoramic pictures. The first track shown here is for a glass material, which is a brittle material, and the second track is for Eagle Ford E rock sample, which is a carbonate-rich organic-free sample. So for the glass material, as I increase the load from left to right, initially I noticed these circular cracks, and this relates to tensile fracture formation, which is a mode 1 fracture. I do not see this type of fractures in the Eagle Ford E sample. This is due to rock needs some confinement before fractures is observed. As I keep increasing the load, I start noticing these lateral cracks, chipping, and spallation, and this is due to the shear stresses ahead of the indenter, and this is related to mode 2 fractures. I do see this type of fractures on the Eagle Ford E rock sample, so I can identify mode 2 fracture toughness for this rock. The second part to the analysis is to compute the fracture toughness. Classical fracture mechanics like LEFM and coercive zone model consider fracture as a discrete entity. This then leads to discontinuous displacement and singularity. And this is why in my study I consider using phase wave modeling, which models fracture as a diffusive entity, so there's a transition between the broken region and the unbroken region. The governing equation to PFM is this minimization of energy using this potential energy equation, which is just the balance between internal work and external work applied on the body. There are much more equations to develop the analytical solution, which I cannot show here due to the time constraint, but basically they are the energy densities, linear momentum, phase field evolution, and fracture geometry. For mode 1 fracture, I consider this quadratic form of fracture geometry. Once I do so, I obtain this dimensionless stress-strain curve, which I then relate to my experimental results. In doing so, I consider the concept of strain energy density, which is just the area under the stress-strain curve. And this is the dimensionless area. I compare it to my experimental results. Once I do so, I obtain the mode 1 fracture toughness. Now for mode 2, I consider this linear fracture geometry as shown here. The analytical solution to this is presented by this dimensionless stress displacement. Again, I compare it to my experimental results, and once I do so, I pretty much get my mode 2 fracture toughness. Now that I showed how the analysis worked, I will now talk about applying it to the materials. I first checked the methodology on reference material with known fracture toughness. Again, first I checked the mode 1 fracture segment as highlighted here, and this is the average that I computed under model and the average published in literature. As you can see, it matched very well. And now for mode 2, here is the segment, and the average is this that I computed, and this is the average published in literature. So as shown here, my results match well with literature, which means the methodology I developed works well for both mode 1 and mode 2 fractures. I then implement the methodology on the Eagle Ford sample. Again, for Eagle Ford E, I can only identify mode 2 fracture since I do not see tensile fracture formation at lower loads. The segment I analyzed is highlighted here, and for parallel to bedding, here is the fracture toughness I computed. Similarly, for perpendicular to bedding, I can only identify mode 2, and the results I approximated is provided here. That brought me to the end of my presentation. I have showed you a new method, first one to approximate anisotropic elastic properties from rock cuttings, and also a novel approach of approximating fracture toughness from rock fragments using phase wave modeling and scratch tests. And again, what's different to previous work is that I approximate anisotropic properties from small samples, which could lead to a cost-effective and high-resolution data, which is valuable in this era of digitalization and artificial intelligence. Thank you for your attention. I am looking forward for your feedback and questions.
Hi, Deborah. Excellent presentation. Honestly, I really liked it and enjoyed it. The only question that I have is what's going to be the next step then? Are you going to implement it in the field, or is that will be added like a kind of to the advanced mud logging in such technologies? I can't hear you.
Hi, Deborah, we can't hear you. If you can try again.
Sorry. Hello?
Yes, we can hear you now.
Okay, sorry about that. But yeah, so right now we're trying to implement this in the field. So basically we're working with a company right now where we are gonna get the drill cuttings in the field because the study that we did currently is on clint cuttings. So it will be interesting to actually work on how we can treat the cuttings so that we can get the real rock mechanical properties from drill cuttings.
Hello, Deborah. Very nice presentation, very insightful research results. My question is that how is the relation between the adaptation modulus and the stiffness derived? So it's already existing in the literature. You just apply the equations to your research, or you derived it yourself?
Hi, Dr. Liu. Nice to meet you again. But yeah, so how I do, somebody else already derived the equation to relate the indentation modulus from the experiment to the 5 elastic constants. So I used the methodology that they developed basically and implemented to my work. And for the optimization, I have to work around it so that because they haven't really done the optimization to identify the stiffness matrix. So yeah.
Thank you. Good work.
Hi, Deborah. Great presentation. So I'm kind of curious. Is there any limitation, especially with regards the depth of investigation of the methodology that you used? Because I believe that there are some other methods that could tell us much more about what's going on. Maybe if there's heterogeneities in the formation. So I'm just curious as to what's your feeling about limitations and depth of investigation. Thank you.
Thank you, Dr. Rita. Yeah, of course, my work has some limitation to it and other works have some advantage to it. To my knowledge, I am the first one, though, that identify anisotropic properties from rock cuttings. The limitation would be that because, like I said in my presentation, there's a high likely chance we don't know the bedding plane orientation. So right now I'm limited in terms of the optimization time that it takes for my program to actually identify the 5 elastic constants. So the current program that I developed, because of the high degree of unknowns, it's very slow. For the work itself, it took me about a month to optimize like 10 results from 10 cuttings. So if I know somebody that can like speed up the optimization process, this can be implemented very easily. So what I've done currently right now also, if I know that bedding plane orientation, the optimization becomes much faster. It took me only 4 hours to get a result from this testing. So that's the limitation that I know of. And like I said earlier, the other limitation would be is like how we treat the cuttings, because in reality, the cuttings are affected by the drill mud. So how we treat the drilling mud also it might gonna affect the rock strength, the actual rock strength of it. While coarse, I think, is a lot more cleaner compared to drill cuttings. So those are the limitations that I know of. Thank you.
Thank you.
So can you hear me, Deborah?
Yeah, Dr. Kumar.
Yes. So I guess it's very interesting work, and thank you very much for a very nice presentation. My question to you is that in trying to apply the small fragments that you have, first of all, these fragments, how are you going to determine the orientation of the fragment within the bedding itself, and whatever is happening, the heterogeneity and anisotropy that is happening within the bed? How would you correlate the two things?
That's a very complex question you get there, Dr. Kumar. Yeah, for the difference between the scratch and the indentation is that for the indentation, like we don't really need to know the bedding plane orientation. And you brought out a good point where for the scratch, in order for us to know the true fracture toughness of it, for this methodology to work, we have to know the bedding plane orientation. And the only way that we have to do that, we can identify the bedding plane orientation if we have rock fragments, not rock cuttings. So by rock fragments, it's like that means it's like somewhere above 1 centimeter. And I can inspect it with a naked eye, just like looking at the cuttings and stuff, it's identifiable. Or we can also go under SEM or optical camera system to identify this bedding. So yeah, bedding plane orientation do affect fracture toughness. So for scratch tests, we do need to know the bedding plane orientation. I hope that answered your question, Dr. Kumar.
Yeah, it does. And thank you. And the second question is, from what you have learned so far, how would you advise somebody who's planning or designing a frac treatment for these kind of rocks?
Okay, that's a tough question. To be honest, I'm not knowledgeable with hydraulic fracturing treatment. I'm still, I don't have an answer to that, to be honest. So that will be something that I'm probably gonna have to discuss with the field people once I get into it and understand it, basically.
Okay, thank you very much for a good presentation. Excellent presentation.
Any further questions from the judges? Okay, so with that silence, we will take that as no more questions. So thank you, Deborah, for your presentation. So this brings us to a close of the first half of the student paper contest. So we are now going to give you and all the judges a well-deserved break. So we will be starting the next series of presentations at 4:40 Dubai Gulf Standard Time. So that's 4:40 Dubai Gulf Standard Time. So that's just 1 hour from now. So we will now be taking a break. So thank you so much. Thank you, Deborah, for your presentation. So this brings us to a close of the first half of the student paper contest. So we are now going to give you and all the judges a well-deserved break. So we will be starting the next series of presentations at 4:40 Dubai Gulf Standard Time. So that's 4:40 Dubai Gulf Standard Time. So that's just 1 hour from now. So we will now be taking a break. So thank you so much. Hello, all judges and participants. So I'm just checking that everyone is here. So we're about to start in a minute or so. Just giving you time to just settle back in again. Okay, thank you so much. I am going to share my screen and start the second session of the SPC contest. Thank you. So welcome back, everyone. We have 6 more presentations for this afternoon session. If everyone is ready, we will now start with Gang Yang, winner of the Mid-Continent North America paper contest.
International gas in July. consistent reservoirs. Thank you very much. Hello, everyone. Thank you very much to be here for my presentation. I'm really glad to be able to present at the International Student Paper Contest. My name is Gang Yang. I'm a PhD candidate at the University of Kansas. The topic I'm presenting today is the minimum miscibility pressure of gas injection in unconventional reservoirs. Here is the outline of my presentation. I'll start with the introduction, followed by phase behavior in unconventional reservoirs. The third part is the minimum miscibility pressure, MMP, in unconventional reservoirs. And I will wrap it up with summary and conclusions. Pore size distribution research demonstrates that the unconventional reservoirs are predominantly consisted of micro to mesopores. Because the pore size and molecule size are comparable to each other, it will have influence on the properties of the confined fluids. That's why it is important for us to know how to characterize the nanoscale confinement and how it will influence the phase behavior and minimum miscibility pressure in unconventional reservoirs. These are all highly intriguing and practical questions we are going to answer in this work. Because of the strong nanoscale confinement, the confined fluid phase behavior demonstrates significant deviations from that of bulk fluids. This includes the suppression of the melting temperature, the saturation pressure shift, the two-phase diagram shift, and also the capillary condensation phenomenon, which is unique for confined fluids. So far, there are two main categories of methods that can be used to characterize the nanoscale confinement. The first is the experimental methods, which include 4 subcategories. The first is nanoscale isotherm adsorption. The second is differential scanning calorimetry. Third is the nanofluidic trip, and also the microscopy methods. The first method can be used to investigate the capillary condensation phenomenon, and the nanofluidic trip and microscopy methods can be used to directly observe the phase transitions of confined fluids in nanopores. Because the experimental methods is not the focus of this work, I'm going to go directly to the theoretical methods, which includes the molecular simulation, the density functional theory DFT, and the extended modified US models. Because the first two methods are more applicable for simple systems at small scale, so the extended modified US model is the focus of this work because it can potentially be applied for a field application. Due to the significant deviations of the confined fluid phase behavior, the classic US models are not applicable to characterize the confined fluids. That's why these models, especially the PRUS, have been modified or extended in terms of the molecular wall interaction, critical property shift, capillary pressure, and also adsorption. The general conclusions include the shift of critical pressure, critical temperature, the two-phase region shrinkage, and also the shift of bubble point and dew point. These are some of the typical examples of the modified or extended PRUS. And one obvious limitations of the current work is that the confinement effect on the effective molar volume, which is convolume B, has not been considered. This is what we are going to do in this work. A key part of this presentation is the minimum miscibility pressure. It is defined as the lowest pressure under which a gas develops miscibility with reservoir oil at reservoir temperature, and it is a significant parameter for the miscible gas injection EOR in unconventional reservoirs. That's why we need to find ways to accurately determine this value. So far, there are also two types of methods that can be used to determine MMP. First is experimental measurements, including the slim tube experiments, the rising bubble apparatus, and the vanishing interfacial tension (VIT). All of these methods have been applied for the determination of MMP in unconventional reservoir fluids. However, all of them have been conducted under bulk conditions with no confinement considered. This leads us to the theoretical methods, which include the slim tube simulation, the VIT simulation, the multiple mixing cell MMC method, and also the empirical correlations. Some of these theoretical methods have been applied for the MMP determination of confined fluids with confinement considered. However, due to the lack of solid validations, the accuracy of these theoretical methods cannot be guaranteed. So the limitations of the current work is, first, the confinement on the effective molar volume is not considered, and second, the minimum miscibility pressure in unconventional reservoirs is not well determined. The research objective of this work are twofold. First is to propose an improved US model to characterize the confined phase behavior, and second is to find accurate theoretical methods to determine MMP in unconventional reservoirs. The second part is the phase behavior in unconventional reservoirs. Basically, we are going to propose a modified PRUS model that can be used to characterize the confined fluid phase behavior and also can be further used to determine the MMP in unconventional reservoirs. Because of the strong nanoscale confinement, confined fluid phase behavior demonstrates significant deviations from that of bulk fluids. In order to figure out the reasons behind that, we can start from the ideal gas law, where the gas molecules are regarded as a mass point without any interactions between each other. When it goes to the real gas, two factors need to be considered, where A is the intermolecular interaction and B is the co-volume. These two are combined as the real gas effect. When it goes to the confined space, two additional factors need to be considered. One is the molecular wall interaction, and another one is the geometric constraint of the confined volume. And these two are combined as the confinement effect. Based on this theory, we can propose a modified PRUS, where C and beta are introduced into the original PRUS, and C stands for the molecular wall interaction, and beta is the co-volume ratio of the confined fluids. After getting C and beta, we can determine the modified PRUS for further application. As for how to get beta and C, I'm going to explain it in the next slide. This is the original PRUS. This is the modified PRUS. These are the equations to calculate AB, AC, and BC. And these are the values to calculate the critical temperature, critical pressure at bulk and confined space. By combining these four equations, we can calculate the expressions to calculate the delta T star, the critical temperature shift, and delta P star, the critical pressure shift, which can be calculated by the bulk value minus the confined value divided by the bulk value. By combining these two, we can get the expressions to calculate beta and C. As we can see, in order to do that, we need to have both critical temperature shift and critical pressure shift data. In order to do that, we collected 58 critical temperature shift and 34 critical pressure shift data from different references, including both experimental and molecular simulation data. By using curve fitting method, we can get the correlations between the delta T star and delta P star versus the dimensionless pore size, which is defined by the pore size RP divided by the molecule size. As we can see, at the same dimensionless pore size, the shift of the critical pressure is obviously higher than that of the critical temperature. And also, the critical pressure shift data are more widely distributed along the fitting line, which means that it is of lower accuracy compared with the critical temperature. In order to demonstrate the accuracy of the newly proposed correlations, we compared these correlations with previously widely used correlations. And as we can see from these two tables, we calculated the critical temperature shift and critical pressure shift data of different fluids at different pore sizes, with both correlations of this work and the correlations of previous work. These are the calculation errors of critical temperature, and these are the calculation errors of the critical pressure. And we can see that the calculation errors of this work are obviously lower than that of the previous work. This is true for both critical temperature and especially for critical pressure. So this means that the proposed critical shift correlations in this work are more reliable than the previous correlations. By incorporating the newly proposed correlations to the modified PR-US, we can get the final expressions for the US model, which can be used to characterize the nanoscale confinement, and it is also applicable for hydrocarbon mixtures with mixing rules. This is an algorithm that can be used to calculate the confined phase diagrams at different pore sizes. In order to demonstrate the application of the modified US model, we collected an EagleVault oil sample from a previous literature. These are the fluid components and properties, and these are the binary interaction parameters. By using the modified PR-US, we calculated the phase diagram at different pore sizes. As we can see, with the decrease of the pore size, the two-phase region becomes smaller and smaller. The third part is the minimum miscibility pressure in unconventional reservoirs. Basically, in this part, we compared the accuracy of different theoretical methods in determining the MMP in unconventional reservoirs. Two main methods have been investigated. One is the VIT simulation, and another one is the multiple mixing cell method. The first method is a VIT simulation, which is highly similar to the VIT experiment, where the interfacial tension IFT is measured at a sequence of pressure. After plotting the IFT versus pressure, we can extrapolate IFT versus pressure to 0, and that value will be the minimum miscibility pressure. For the VIT simulation, instead of measuring the interfacial tension value, it is calculated by the empirical approach algorithm that is demonstrated here. One thing I need to point out is that the fugacities of both liquid and vapor phase are calculated by the modified PR-US to reflect the effect of nanoscale confinement. The second method is the MMC method, which is based on the modification of a previous algorithm. This is a demonstration of the multiple mixing process, where we start from injected gas and crude oil. By mixing these two, we can get new liquid and vapor compositions, and we keep mixing until the nth contact. We have n-1 pair of x and y values, and each pair of this x and y can be used to calculate the tie line length. And among these n-1 values, we can find a minimum value, which is the minimum tie line length. We can store that value under that pressure, and after updating the pressure value, we can find a new minimum tie line length, and we keep doing that until the minimum tie line length is highly approximating 0, and that pressure is MMP. There's also one thing I need to point out here is that the vapor-liquid equilibrium calculation is conducted by the modified PR-US to reflect the nanoscale confinement. In order to demonstrate the accuracy of these two theoretical methods, we compared their results with the experimental measurements. For the experiments, it is for a binary mixture CO2 plus NC10 at bulk and 50 nanometers. These are the values of the experimental measurements. These are the values of VIT simulation. And these are the values which is calculated by the MMC method. These are the calculation errors of VIT simulation, and these are for the MMC method. As we can see that these values are much lower than the VIT simulation. So it means that the MMC method is much more accurate than the VIT simulation in determining the MMP for confined fluids. To further demonstrate that, we also calculated the MMP of the binary and quaternary mixture at different pore sizes with both VIT simulation and MMC method. These are the calculation errors of the VIT simulation, and these are the calculation errors of the MMC method. As we can see, these values are much lower than these values. It means that the MMC method is much more accurate than the VIT simulation. By using the MMC method, we also calculated the MMP values of both bucking oil and Eagle Ford oil at different pore sizes with different injected gases. Because in real field scenarios, different gas or gas mixtures may be injected for the UR purpose. So from these values, we can conclude these 4 points. First is that the calculation results are close to measured values, and also MMP is drastically suppressed within nanopores, because with the decrease of the pore size, the values, MMP values, become smaller and smaller. Third, the MMP values of Eagle Ford oil on the right side are much lower than those of the bucking oil, and also the mix of CH4 into CO2 can either decrease or increase MMP values. As for bucking oil, it increased, and as for Eagle Ford oil, it is decreased. So this leads us to the summary and conclusions. First is that the modified PRUS model is applicable to characterize the confined fluid phase behavior. It can also be further used to determine the MMP values. The phase diagrams of the confined reservoir fluids tend to shrink with the decreasing pore size. And at the same dimensionless pore size, the critical pressure shift is higher than that of the critical temperature. Compared with VIT simulation, MMC method is much more accurate in determining the MMP on conventional reservoirs. MMP of confined fluids are drastically suppressed within nanopores, which is favorable for the miscible gas UR in conventional reservoirs. With a mix of CH4 into CO2, the MMP values can be either decreased or increased, depending on the compositions of the reservoir fluids and injected gases. With that, I'd like to acknowledge the support from KU Chemical and Petroleum Engineering Department, and I'm happy to get any comments and questions. Thank you very much for your attention.
Thank you very much, Gang, for your presentation. We would now like to welcome the judges for any questions.
Hi, Gang.
Hi.
Thank you
Hi,
for
Rita.
that excellent presentation, and well done. So I'm kind of curious, you saw that the critical pressures that, it was much higher, the errors when computing the critical pressures, that delta P was much higher, even in your method, in the other methods. Could you just share with us your thoughts on why you think that is the case? Why are we having high errors with the delta PC?
Okay. First, yes, as we can see that calculation errors of the critical pressure is much higher than the critical temperature. And the reason for that is because in this paper, I used the curve fitting method to get the correlations of P star and T star versus the dimensionless pore size. And the first thing is that for critical pressure, we have limited data points compared with that of critical temperature. That's the first thing. And this will cause the curve to be less accurate. And the second reason is that for the critical pressure, it is more influenced by the heterogeneity of the pore. For example, the pore chemistry or the roughness of the pore surface, and but those kind of parameters haven't been considered in those data points. So this may also cause higher inaccuracy for the critical pressure.
All right, thank you.
Thank you.
Any further questions from our judges?
Anil, we can't hear you.
Sorry, yeah. So thank you again, Dr. Yang. And I wanted to ask you, so what is the physical significance of suppression of this critical pressure?
Could you please repeat your question?
Okay, my question is that we're observing a suppression of critical pressure, delta P star. So what do you suppose is the physical significance there? What is actually happening? Molecular, I mean, in terms of molecular interactions.
In terms of what?
Molecular interactions. I mean, at that level, you're observing, due to results of confinement, you're finding a change, suppression in critical pressure. What is really fundamentally going on there?
This is a very good question. Actually, it really goes deeper. I think what really happens is that because for in bulk space, the interaction between the molecule and the pore surface is usually ignored because it is really small compared with the interaction between the molecules. And then when it goes to the confined space, or I can say nanopores, the interaction between the molecule and the pore surface are quite stronger. And mostly, based on my calculation, mostly the interactions are attractive. So that confinement will cause the fluid to be easier to convert it to critical fluids. Supercritical fluids.
Okay. Excellent. So yeah. So also help me understand, how do you determine beta in your calculations, in your mathematical model? I mean, how do you determine beta in your in your mathematical model? Is it determining beta, the long beta?
Should I go on, or because the time is running out? I can state it pretty simply, because as you can see, we introduced two parameters, C and beta, And
Right.
then both of these two parameters are calculated by the critical temperature shift and critical pressure shift, actually.
Oh, okay. Okay.
Yeah,
So
we build those correlations, and then we input those correlations to the two expressions to calculate the beta and C, and then that will give us the final result of beta if you have the pore size and the molecule size over there.
okay. So you're not actually doing, so beta is actually determined explicitly. It's not implicit. It's not a a reversion process or something that you're trying to find a match.
No, when you have the specific molecule, when you have the specific pore size, you will get explicit beta value and C value.
Okay. Thank you.
Thank you.
Any further questions from our judges? Okay, so with that silence, I will take it as no further questions. So we will now move on to the next presentation.
Thank you.
Thank you so much for your presentation, gang. Thank you. So we now move on to Oscar Enrique Medina, who won the Latin America and Caribbean paper contest.
Dear judges, dear attendees, thank you for being here today to attend my presentation as part of the SP International Student.
Sorry, please accept my apologies. I have given out the wrong name. Sorry, I do apologize. The next participant is Abdurrauf Chenmak. I do apologize. My apologies. So Abdurrauf Chenmak, winner of the Rocky Mountain North America paper contest. Thank you.
Paper contest. I will be presenting today a study about machine learning predictive models to estimate the uniaxial compressive strength and tensile strength of rocks in Bakken Field. My name is Abdurrauf Chenmak and I am PhD student at the University of North Dakota. The presentation outline will be as follows. I will talk briefly about uniaxial compressive strength and tensile strength and the conventional approach used to determine them. Then, I will introduce the new approach for uniaxial and tensile strength determination. After that, I will clarify the process for developing the new models and how to validate them using proper tools. The next step is the most important one, where I will talk about the ability of the new models to estimate the UCS in Bakken Field and discuss the obtained results. Finally, I will end up my presentation with a conclusion and findings for our study. Uniaxial compressive strength, or UCS, is the ability of rocks to resist compression, meaning how much load it can resist until it fails, while the tensile strength, or TS, is the ability of rocks to resist attraction. The proper determination of these parameters is critical for drilling operations and geomechanics when it comes to wellbore stability, rock classification, and failure criteria. Conventionally, the UCS is determined in laboratory using destructive tests such as the uniaxial loading test, or some faster but less accurate methods such as the rebound hammer. On the other hand, tensile strength is measured indirectly using the Brazilian test, as shown in the picture presented on the slide. It's worth to mention that these tests are expensive and time-consuming, which makes it inconvenient to use them consistently. As an alternative, the use of correlation elaborated in specific field conditions could be acceptable for a case of similar parameters range. Any further extrapolation of these models lead to significant errors. Now, with the development of mathematical tools, the use of machine learning algorithms has become quite popular due to their ability to recognize patterns capture nonlinearities, and the interdependence between the parameters. The first part of our study consists of developing artificial neural network and a seaport vector regression model for uniaxial compressive strength, then validating the models with results comparison, and following the same analogy to elaborate the models for tensile strength. The second part of the study was to test the accuracy of the models developed for uniaxial compressive strength on back and field data. The first dataset used for this study was collected from literature. It is for 200 samples for 4 different rocks, namely limestone, slate, quartzite, and quartzite mica schist, collected from the Luri area, Himachal Pradesh in India. The inputs selected for the models are P-wave, cohesion, density, and the friction angle, in order to have a clear idea about the distribution and ranges of the data. The distribution histograms shown in the slide clearly demonstrate the wide ranges of data used. For example, the range of UCS values is from around 40 up to 250 megapascal. In order to have an idea about the interdependence of the parameters, the heat map presented in the slide shows that the P-wave, for example, is correlated with uniaxial compressive strength with a coefficient of 0.98, which means that the selected inputs have strong relationship with the outputs. Any changes in them affects UCS and tensile strength directly or indirectly. Moving to the developed models, the first one consists of building an artificial neural network, which consists of an input layer that contains the input parameters, here we're speaking about P-wave, density, and so on, and an output layer which contains the results that we are looking to estimate, UCS or tensile strength in our case, and a set of hidden layers composed of neurons where all the operations of the model are conducted. Now, let's explain a little bit how the algorithm works. All the work is done by minimizing the error between the predicted UCS and the experimental values of UCS. Then, we keep adjusting the algorithm by changing the architecture and the number of neurons in each hidden layer until we reach the results we are looking for. What happens inside each neuron is that it receives a signal from a previous layer, transform it by an activation function, in our case it's rectified linear unit, then it multiplies it by some weights. The process is repeated for a number of iterations until the error between the two UCS values is minimum. To ensure that the model is valid, the data is divided into a training set to train the model and a testing set to which the model will try to predict the test accuracy. The ratio in our case was 80 to 20%. As we mentioned, the structure of the algorithm plays a huge role in its efficiency. For this reason, a sensitivity analysis was performed to choose the best architecture of the neural network. For uniaxial compressive strength, the architecture was one input and output layer and 6 hidden layers with 10 neurons each. And for tensile strength, 6 hidden layers with 20 neurons each. The whole sensitivity analysis is presented in the paper. The second model consists of a seaport vector regression. This different type of regression has mainly 3 parameters to adjust in order to obtain good estimates of either uniaxial compressive or tensile strength, which are C, epsilon, and gamma. The mathematical description of each of them is presented in the paper. Now, to find the best combination of these parameters, either we do a trial and error process which takes time, or we use an algorithm such as the genetic algorithm that makes the optimization automatic by involving the operations of selection, crossover, elitism, and the mutation. And the process is repeated until the criteria is met. Now, what do we mean by these parameters? Is that the algorithm uses a set of solutions and tests their accuracy. If the criteria is not met, it selects the best solutions and combines them to get a better results. One interesting step is to perform a mutation, which means introducing new solutions each time in order to avoid stacking in some local minima in case there are any. As previously done with artificial neural network, the data was divided into a training and a validation dataset with a ratio of 80 to 20%. The combination of these values for each algorithm has presented in the paper. The results of both models are compared to validate the models. The comparison was based on statistical parameters used by machine learning practitioners to validate the models, namely R2 score or the R squared. Here, a 0 value means that there is no match, and a value of 1 means a perfect match. A root mean squared error and a mean average error. Here also, a 0 means there is no error between the actual and predicted values. Now, for uniaxial compressive strength, the values presented in the tables for both training and the whole dataset clearly demonstrate the good performance of the models in predicting UCS. I mention here, for example, the R squared for the artificial neural network for the test set is 0.995, which is a very good value. Another example is mean average error for the support vector regression for the test set, which is 1.1, means that the error expected in UCS values is around 1.1 megapascal. To have an idea about the nature of the errors, the error distribution histograms are shown in the slide, proves that most of the errors are placed around 0, which means the values of UCS are well predicted. The same analogy was followed for tensile strength. The values presented in the tables, along with the error distribution histograms, shows that the models are powerful and can estimate the tensile strength in a proper way. We take, for example, the value of mean average error of the test set for the artificial neural network, which is 0.35. This means that the average error in predicting the tensile strength values is around 0.35 megapascal. Now, after developing and validating the models with data from one region, the next step is to apply this model on a very different data from another region and test their efficiency. The data selected is from Bakken Formation in Williston Basin, which is located between North Dakota and Montana from United States and Saskatchewan from Canada. 240 core samples from middle, upper, and lower Bakken were prepared to perform rock strength testing using the AutoLab. Concerning the study, a rigorous data cleaning was made to make sure to collect only consistent and accurate test results. We were able to obtain 20 lab test results for core samples with uniaxial compressive strength values, which means that we will assess only the models developed for uniaxial compressive strength. To get a clear idea about the new data obtained from the Bakken field, some statistical analysis is performed and compared with the data from Luray area, as seen in the graph on the left. According to the graph, we can notice that both the inputs and the output of the model are different in terms of the range of values, the mean, and the standard deviation, which means that the new obtained data is different from the first one, and it is a good practice to use it and test the model accuracy and see if it can play as a universal model or just a local model. Then, the heat map on the right is showing the correlation between the input parameters and UCS. While some parameters present the same trend as before, the angle of internal friction has changed the trend, and it is inversely related to UCS now. We relate this change to the heterogeneity of the Bakken formation, which makes the prediction of UCS more complex. After applying the models developed on this data, the results were compared with commonly used correlations from literature. We selected 2 linear correlations and 2 power law correlations as presented on the slide. The results are presented in the table as shown on the slide also. Finally, to have a better understanding of the obtained results, the predicted values are plotted against the original values of uniaxial compressive strength for each model. As seen in the graph, both correlations of Horsehead and Kahraman, which present the power law models under predicted DUCS values, given values mostly between 60 and 80 megapascal, which gives poor performance of the correlations, having a very low R2 score and significant errors as presented in the graph on the left. On the other hand, the linear correlations of Handelwell and Sharma over-predicted the UCS values, placing them in a range between 200 and 500 megapascal, performing poorly as well on the backend data, having very low R2 score and significant errors as presented on the graph on the left as well. Contrary, the proposed models of both artificial neural network and support vector regression predicted the UCS values in a very acceptable range. The resulting values of R2 score are 0.93 and 0.92 for both models respectively. The range of errors is between -20 to +20, with most points located around 0 as presented in the graph. Also, we have small values of root mean squared error ranging from 7 to 9 and mean average error ranging between 9 to 11 as presented in the paper. All of this talking leads us to conclude the study by the following. 2 machine learning algorithms were developed, both artificial neural network and a support vector regression, to predict uniaxial compressive strength and tensile strength. The inputs included in the models are p-wave velocity, the density, cohesion, and the angle of internal friction. The models are trained and developed on data from the Lurie area in India and applied on the data from the Bakken field in the United States. The obtained results for both models showed strong performance in predicting the values of both uniaxial compressive strength and tensile strength. The presented results make the developed models universal up to some extent. At the end of my presentation, I would like to express my gratitude to Dr. Rasoli and Dr. Ling for their inputs along the course of this work. Thank you all for listening, and I will be happy to answer any of your questions.
Thank you. We would now like to invite the judges to any questions.
Hey, oh, can I go first?
Yeah, go ahead, please.
Okay, thank you. I have a quick question. Is that why you choose 6 layers in your ANN model?
Okay, thank you so much for your question. Well, as I mentioned in the slides, the trial and error process was chosen. So we tried multiple number of hidden layers with multiple neuron number in each time. And based on the performance of each architecture of the model, the final one was chosen. As a matter of fact, I presented on the paper that we submitted a whole sensitivity analysis speaking about this one.
Okay, thank you.
Sure, thank you.
Hey, a very nice presentation. I have just one quick question. So why did you choose the SBR regression model, and did you try other regression models?
Okay, thank you so much. Actually, this is very good question. Why is that? Because when we speak about regressions, the conventional approach is either the linear or the nonlinear regressions. But when it comes to support vector regression, it actually takes the regression to another level, where it takes the nonlinear problem into a higher nonlinear degree problem. How is that done? Is by presenting the problem as kernels, then matches, then takes the inputs and tries to, instead of minimize the error as the simple regression does, it places the error in a range that we give it. So it is like an engineering based range. So if we tell the algorithm that we can accept like -5 plus -5 or +5 megapascals in your calculations, that will take that as the boundary. Then what it takes, it multiplies all those inputs by the three parameters that contains the model, which we optimize by the genetic algorithm, which are the C, epsilon, and gamma. Here we have to speak about the mathematical definition of each one, but in the formulation of transformation between the linear to the nonlinear procedure, each parameter has a significance. For example, the C will have the weight of the difference between the value that we have as the experimental and the value that we are predicting. The alpha will take into consideration, the gamma will take into consideration how much error that we are accepting, and the same for the epsilon.
Thank you so much.
Sure.
Hi, Abdel.
Hey.
I have two questions for you. Great presentation. So the first question I have has to do with, you know, when you compared the ANN and the SVR to the correlations, and you could see this big shift in how, in fact, the correlations fail. So could you just provide to us some insight as to why these correlations were not suitable for predicting the UCS of the backend field? So that's the first question. The second question is, you built your model based on data sets from India, that you started the model based on data from India, and then you applied that algorithm, as it were, based on what I listened to in the presentation, on the data in the backend field. So did you tune your model, any of the parameters of your model, to be able to fit the data for the backend field, or was it just as the model was, it was a perfect fit for the backend field? Perfect fit for the backend field. Yeah, thank you.
Okay, thank you so much. Those were like very precise questions. As the first part, the correlations I chose are obviously from literature. So what I did is I took random correlations that are used in not in specific fields, but are widely used. Here, what comes the difference? When we applied these correlations on a specific data from the backend, they fail to predict like the good values. One reason for that is, as I mentioned, these correlations are developed on a specific field conditions, which means when we extrapolated the results to the backend field, which has like a different trend, the different values for UCS, different values for P-wave, the correlations either failed to capture that or overestimated that in the case of the linear ones, or underestimated that in the case of power law models. I hope I got the answer for your first question. The second part of the question is what is really interesting about this study. So the models were developed on the first data set from India without touching the models, without tuning them at all. We just applied those models on data from backend field. And this is what actually makes this study interesting, because without tuning the model, without just interfering, and without doing any model tuning or those mathematical manipulations, the model could predict the values for the backend field UCS. Now, what's interesting about this is that we're emphasizing here on the use of machine learning, since we are using either ways a mathematical tool such the correlations. And here we're using the machine learning models to get a very accurate results with very, very less time and effort consumed to get these results. One way we can take this study up to another level is to get data from a different region and test these models and see their accuracy. As I mentioned here, we claim that these models may be universal, but a next step would be test these models on very different data, for example, from the Middle East or North Africa.
All right, thank you.
Sure, thank you so much.
Any further questions from the judges?
Yes, so Abdul, thank you for a very interesting presentation. So I'm interested in knowing why do you suppose this test data from this Indian field worked out so well for Bucket?
Sorry, could you repeat that one?
Okay, so the question is that the test data that you got from this Indian field turned out to be so well for Bucket. You know, have you applied it to say Eagleford or some other formations to see if the same test data will work for other formations as well?
No, actually, this is the data that I got my hands on. This will follow up the answer to the previous question by the previous judge. The next step of this research is to apply to a different data, for example, Eagleford or a different formation. One good estimation is that the model can give results and can give good estimate of these values as it did with the Bakken field, since the model was trained on data from India and has no information basically on the data from the Bakken field. I believe that it will give the same results if we test it in a different data or on different formation. But the only thing that will prove this one is to do more investigation by getting hands-on data.
So the follow-up question would be, so do you think the range of the test data, from this field in terms of P-wave and density and other parameters, is it similar to what you're observing in Bakken?
Actually, it is not very. It's not very likely, or it is different in other words, because in the slide I presented the statistical analysis in terms of the minimum and the maximum of the values, where it was different in the India field than the Bakken, and the standard deviation of the models also in terms of the mean. The research is more of data driven, and looking to the data in the Bakken field, it says clearly that it is different from the one in India.
Thank you. Excellent.
Sure. Thank you so much.
Okay, so that concludes our Q&A session for Abdurruth's presentation.
Thank you so much.
Thank you so much for your presentation, Abdurruth. So we will now move on to the next one. Oscar Enrique Medina, who won the Latin America and Caribbean paper contest.
Good day to all judges. I am Oscar Medina, and for me it's an honor to be part of this wonderful event and share with you and the scientific and industrial community part of my doctoral thesis work focused on the kinetic oxidation in sites of heavy crude oil at reservoir conditions to enhance the efficiency of in situ combustion processes. The agenda to present today consists as first of the explanation of the motivation of this work, followed by the main objective, a brief description of the methodology used, the most relevant results and conclusions, the bibliography used to make this presentation, and the respective acknowledgements. Well, this work appears under the need to understand the oxidative behavior of the heavy crude oil to optimize the thermal methods. Because the composition of the crude oil is complicated, it is conventionally divided into saturates, aromatics, resins, and asphaltenes. In the specific case of the heavy and the extra heavy oil, the asphaltenes are found in mass fractions between 3 and 30%. These compounds are the heaviest and most polar fractions of the crude oil, and the location and high content of the heteroatoms in the molecular structure leads to high polarity, which provides their self-assembly characteristics, generating a rigid and stable viscoelastic network that prevents the crude oil flow and making necessary the addition of energy by means of heat to improve the production operations. In this sense, the oil and gas industry has applied different thermal enhanced oil recovery methods, including the in-situ combustion. During the in-situ combustion, the heat is propagated throughout the reservoir by igniting the heavy and the extra heavy oil, injecting air or oxygen-enriched gas into the formation, and subsequently reducing the unborn oil viscosity and improving its flow. However, this technique faces several challenges pertaining to the combustion front instability and the increase in the oil viscosity due to the low temperature reactions. And also, the heaviest fractions are transformed into coke at low temperatures, and a greater number of oxygen-containing compounds are produced. So, to achieve an optimal petroleum operation design, it is important to understand the chemical reactions and the thermal behavior of the asphaltenes in terms of the oxygen addition reactions, the asphaltene chemical nature, and the asphaltene aggregation phenomena. Well, based on this information, this work is interested in the study of the thermo-oxidative decomposition of the heavy oil based on the understanding of the oxidative behavior of the asphaltene model molecules in aggregates. Well, the proposed methodology to fulfill the mentioned objective consists first in the characterization and construction of the asphaltene molecules. For this, the asphaltene isolation was done from 7 different heavy and extra heavy crude oils obtained from different industrial partners around the world. Then the molecules were characterized in terms of elemental analysis, X-ray for electron spectroscopy, X-ray diffraction, vapor pressure osmometry, and nuclear magnetic resonance. And finally, based on density functional theory calculations, the molecules were constructed and fully optimized using the Vickers strip parameter and Lie power functions, and also the Couillard's theory of the aromatics state was used to predict the stability of the aromatic system. Then, to obtain the asphaltene aggregates, different model solutions were prepared by slowly adding a determined amount of the asphaltenes to the 3 aromatic solvents, while the mixture is magnetically stirred at 300 revolutions per minute during 30 minutes. Then the asphaltene aggregate size on the different solvents were registered by a small angle X-ray scattering, and the viscosity was determined by rheological measurements. As for the oxidation experiments, a high-pressure thermogrammetric analyzer was used. These experiments were developed in 3 main subsections studying both the virgin asphaltene oxidation for a single source in a wide range of pressures between 0.084 and 6 megapascals between 100 and 800 degrees Celsius. Then the second subsection includes the oxidation of different sources of asphaltenes at low and high pressure. And finally, the third topic consists of the oxidation of asphaltene model solutions at high pressure to obtain information about the aggregation state influence on its reactivity. On the other hand, molecular dynamic simulations were executed to reproduce the oxidative experiments. To design the p-asphaltene molecules was selected due to its complexity, and for this purpose the reactor field potential was proposed because of this potential employs a bond-order formulas in conjunction with polarized Hilbert chart descriptions to describe the reactive and non-reactive interactions between the atoms. Then, the simulations were conducted using a LAMP software, and the air and the asphaltenes were constructed separately. Also, the reactor field simulation was performed using an MVE ensemble, beginning with the energy minimization of the reaction system. Then, the system was equilibrated at 100 degrees Celsius for 100 picoseconds with a time step of 0.1 femtosecond. The temperature was increased up to 600 degrees Celsius to simulate the heating rate used in the experimental tests. Well, moving to the results, the asphaltene molecules were experimentally resolved, and the results suggest that a structural difference exists between each one of the molecules, checking the parameters obtained experimentally in the different characterization techniques. Some of these properties were found similar for the asphaltenes 1A, A, B, and C. And for example, these asphaltenes present a higher hydrogen-carbon ratio, a higher content of aromatic carbons, a higher distance between zinc-boron aromatic sheets, higher degree of aromaticity, higher degree of condensation, and a higher content of thiophene, pyridinic, and carboxyl groups. Well, moving to the oxidation experiments, one of the first questions that arises is what is the effect of the pressure on the asphaltene oxidation? This figure shows the mass change and rate per mass change profile as a function of the temperature for the asphaltene oxidation at different pressures. At low pressure, it was found that the temperature profile was divided in two main regions, commonly known as first and second combustion. But for pressures higher than 0.7 megapascals, four regions are detected. The first region is named as oxygen chemisorption region, which corresponds to the temperature interval in which an increase in the asphaltene mass is observed. This could be associated with the incorporation of oxygen atoms on its chemical structure from the oxygen-rich environment, and as pressure increases, the oxygen percentage increases too. The second region, known as the decomposition of chemisorbed oxygen region, is the temperature interval where the first decomposition and desorption of oxygenated compounds occurs. That is where the mass sample begins its reduction. And as the pressure increases, this region is at higher temperature since it requires a decomposition of more oxygenated structures. Then, for higher temperatures, the first combustion phenomenon is divided in two main regions that are the first and the second combustion. These intervals were separated according to the thermal event close to the 400 degrees Celsius, clearly observed in this panel. The total consumption of the asphaltene is carried out at the end of the second combustion, and each one of these regions are defined by a particular behavior associated with its mass change and its mass change rate curves at the time of its decomposition in mathematical functions, conventionally Gaussians and Lorentzians, which perfectly describe the area under the curve. Finally, the results suggest that the asphaltene oxidation is a pressure-dependent phenomenon. Once we understand how pressure affects the reactivity of the asphaltenes, it is important to understand its influence from its chemical nature. Here are shown the thermograms obtained at the three pressures evaluated for each one of the asphaltenes. For all cases, it was found that the decomposition profiles are described by the four thermal events previously mentioned. However, some differences were found. The first one is related to the oxygen chemisorption percentage, which was higher for the A, B, and C asphaltenes. And in total agreement, it was found that some properties follow a direct relationship with this variable, including the oxygen-carbon ratio, the carboxyl content, and the aromaticity degree. Other important fact is that the D, E, and F asphaltenes exhibit a considerable increase in the intensity of the peak at 6 megapascals during the first combustion, related to the increase in the collision probability between the oxygen molecules, thus higher kinetic energy triggering rapid exothermic reactions with the aliphatic chains and promoted the asphaltene dealkylation. These results were corroborated with the amount of mass loss of the systems during the first combustion region, where a triple of mass is lost for the D, E, and F asphaltenes compared to the A, B, and C. In addition, the mass loss is correlated with the high aromatic character of the asphaltenes D, F, and E, the total values for the aromatic rings, the thiophene pyridinic content, and the degree of condensation of the samples, which improves the decomposition of the asphaltene at higher temperatures. The third topic of this work is focused on understanding how the asphaltene aggregates behave under an oxidative atmosphere at different pressures. Well, here is shown the results from SACS and experimental relative viscosity for the different asphaltene concentrations dissolved in the P, M, and O xylene. Clearly, the length of the asphaltene aggregate is correlated with the viscosity of the solution models. The viscosity increases as the size of the asphaltene aggregate increases, and in turn the viscosity increases as the asphaltene concentration in the model solution rises. As for the oxidation experiments, the effect of the asphaltene content was assessed using the p-xylene as reference solvent. As a first instance, it is observed that regardless of the asphaltene concentration, the thermograms are described by the four thermal events, that is the OC, DCO, FC, and SC. But interestingly, substantial differences were found in the different thermal stages as the asphaltene content increases. The thermograms shows that the amount of oxygen chemisorphed increases as the asphaltene concentration decreases, which is intrinsically attributed to the size and surface area of the aggregates and the subsequent thermal expansion. The results also suggest that the smaller aggregates present a higher surface area volume ratio, and therefore they present a higher number of active sites for interacting with oxygen, which in turn represents a more representative absorbed mass fraction than when the agglomerates are larger. Well then, comparing with the different solvents used, that is the PM and O-xylene, it is noted that the mass gain in the oxygen chemisorption region for the three systems increases in the order O-xylene, M-xylene, and P-xylene. In this sense, depending on the solvent used, the asphaltenes have greater or lesser interactions between them and the solvent. As a consequence of the mass gain in the oxygen chemisorption, the rest of the thermal events change to a great extent. In the case of the p-xylene with the less values for the oxygen chemisorption percentage, the DCO region ends at higher temperatures compared with the systems in the M and the O-xylenes because of the few oxygenated structures that were formed. Afterward, both the first and second combustion ends up at higher temperatures for the p-xylene system. The main change is observed for the second combustion region, where the profiles for the model solutions of the asphaltenes with the M and the O-xylenes present a small peak between the 400 and 500 degrees Celsius, while in the p-xylene this is the predominant peak in the curve. Finally, the fourth question that was resolved in this work was that if it is possible to describe the reaction mechanisms using an atomistic representation by molecular dynamics simulation. Well, first, the air composition was equivalent to the experimentally used, that is 20.93 of balanced oxygen and nitrogen. The density of the reaction system was set to 0.035 grams per cubic centimeters, and the equilibrium was reached at 1 nanosecond at 3 megapascals. This density allows to the asphaltenes and the oxygen to be fully in contact and ensure that the system remains with the high pressure. Also, as it was said, the V-asphaltene was selected to evaluate and reveal the oxidation details of the experimental test. Well, different snapshots were taken in different temperature intervals to understand the effect of the oxygen in the asphaltene molecule at high pressure. Here is shown the reaction pathway during the oxygen chemisorption region for the V-asphaltene at 3 megapascals. First, it is shown that the oxygen molecule attacks the aromatic ring alpha and breaks its conjugation to form an hydroxyl group and a ketone group. Then, the 6-member ring beta degenerates into a 5-member ring gamma, and then the hydrogen atom on the phenolic group is transferred to an adjacent carbon to form an aldehyde group. At the same time, the sulfur is oxidized to form a dibenzothiophene, and the oxidation of the pyridinic group occurs at the end. Up to this point, the results suggest that the oxidation of the asphaltene mainly occurs on the polyaromatic hydrocarbons rather than on the side chains, indicating that its reactivity is higher. This process can be understood in terms of the localization of the aromatic state in the polyaromatic hydrocarbon, as it was proposed by Clark's theory. Well, before beginning with the explanation of the rest of the thermal events, it is important to show that the thermal profile obtained during the simulations were very similar to the experimental values, verifying the reliability of the real-world field simulation results. Then, based on the simulations, the reaction pathway for the decomposition of chemisorbed oxygen, first and second combustion, was determined. Well, the cracking of the asphaltene begins with the breaking of the sulfur-oxygen bond, followed by the breaking of the carboxyl group in an aliphatic chain, and followed by the breaking of another aliphatic chain. Up to this point, the decomposition of the oxygen-based structure and the dealkylation of the asphaltenes have happened. Then, at higher temperatures during the first combustion, the aromatic core breaking occurred, and then during the second combustion, the breaking of the aromatic core and the aromatic sulfur takes place. Finally, the most resistant functional group to decompose is the aromatic core with a nitrogen functional group, which remains to the second combustion region. Well, in conclusion, this work was focused on understanding the effect of pressure on the thermo-oxidative behavior of asphaltene molecules and aggregates. Both systems showed a direct dependence of the temperature and the pressure of the system. Unlike the low-pressure results, the asphaltenes undergo marked oxidation at low temperatures when the system pressure is higher than 0.7 megapascals. Also, it has been observed that depending on the chemical structure that asphaltene acquires in the oxygen chemisorption region, its reactivity changes in the rest of the thermal events. On the other hand, the interactions between the oxygen and asphaltenes depends on their chemical nature, so it's really important to know the composition of the crude oil in the field in which an in-situ combustion will be carried out and determine the best operating conditions to avoid the exothermic and violent reactions during the first combustion region. Also, the interactions between the asphaltene molecules gains importance at high pressure, since depending on the size of the aggregates, the reactivity of the asphaltenes could be decreased. As for the dynamic molecular simulation, the reservoir field potential allows a description of the breaking and creation of bonds to propose a precise and detailed reaction mechanism for the asphaltene oxidation at high pressure conditions. So, a new landscape has been opened with the explanation that the asphaltene oxidation is controlled by the sequential reaction mechanisms which change under high pressure conditions. So it is really important to consider all this analysis to understand the thermal mechanisms that can affect in situ combustion process and thus be able to develop the technology with more cost-effective benefits. Finally, based on all these results, I have been advancing in the understanding of the oxidation mechanisms to optimize the in-situ combustion process, also in the study of the catalytic oxidation of the asphaltenes using different nanocatalysts at high pressure condition. Also use the asphaltenes to produce more valuable products during the oxidation behavior such as the hydrogen, and also the possibility of the crude oil upgrading during the asphaltene decomposition in the presence of the nanocatalyst. Finally, we are working on the upscaling process with a big oil Colombian company, and it is expected that the pilot test will be done in the middle of the next year. This was the bibliography employed to construct this presentation. And I like to acknowledge the professors Camilo Andrés Franco, Farid Cortés, Iván Moncayo, Nazar, as well as the Grupo de Investigación en Fenómenos de Superficie, Michael Pulangi, for their valuable recommendations and support.
Thank you. So now we would like to invite the judges to ask any questions.
Rita, please, you can go.
All right, so Oscar, thank you very much for such a beautiful presentation, very interesting. Now, you've looked at several processes and mechanisms in the course of your presentation. What would you say, I mean, if you had one of these processes, one of these parameters that you've looked at, what would you say is the most significant of these if you were to advise an operator to take an action while trying to develop a field, a heavy oil field. So what would you say is very significant based on what you studied? Thank you.
Thank you for that question. I think that this was the first approximation reported in the scientific literature, which used the molecular dynamic to describe the crude oil oxidation based on the asphaltene interactions at reservoir conditions, right? So also we try to use the experimental tool to give a novelty of this work that is the evaluate the effect of the pressure on the reactivity of the asphaltenes, right? So it will allow to a better explain of the reaction pathway that these molecules undergo at reservoir conditions, which further could be used to optimize the oil recovery process. Among the main results, I can say that the first one is that we discovered two new regions that never has been that has never been seen during the asphaltene oxidation, that are the oxygen chemisorption region and the decomposition of the chemisorped oxygen compounds. And we understood that these regions are really important when we are trying to oxidize the crude oil at the reservoir condition, right? Because as the pressure increases, the interactions between the asphaltene molecules and the oxygen molecules gain importance. So when the pressure is higher enough, we can reduce the activation energy and the energy requirement to carry out the total decomposition and the molecules. And also, if we have a deeper understanding of the chemical nature of the asphaltenes and the crude oil in general, we also can optimize how we can be realized and thermal enhanced recovery process, and specifically an in-situ combustion process, because we can control how the first and the second combustion will be carried out. As if we know, if an asphaltene has, for example, a short aliphatic change, with total security will be carried out an exothermic and violent reactions at this during this transition from the first to the second combustion, right? So we need to optimize how we can control that pressure in the reservoir to avoid these cases, and avoid, for example, the instability of the combustion front, right? I think that that's all that I can say about the question. Thank you so much.
All right, thank you.
Oscar, thank you so much. Excellent presentation. I have a couple of questions. The first one would be, I assume that you noticed secondary reactions while you were studying the mechanism. So would you please comment on that, the secondary reactions, how you would control them in such a convergent process? And the second question regarding to your way forward steps, I saw that you would consider the catalytic conversion. So what would be the best catalyst in this case? How you would design it in order to avoid the blockage of the catalyst? Are you going to consider heterogeneous or homogeneous catalyst? That's all. Thank you again for the great presentation.
Thank you so much for your amazing question. Okay, well, from the first question, I like to highlight what is the importance of the reservoir field potential. This potential, in fact, allows the analysis of the breaking and creating bonds based on bond orders, which is the coordination number of the molecules, which can allow us to determining what type of order of each atom and bond has. Like it is unstructured, is a sigma bond of pi or double pi. So the difference that the conventional dynamic simulation, the boundary walls and the column energy that are only understood during the conventional dynamic simulation, here we are considering the energy of the structure of the molecules that are associated with the angles, with the diagonals, and etc. So during the reaction pathway, it was determined, and the interactions between each one of the atoms that were parameterized for the asphaltenes and for the air. So we have 5 atoms for the asphaltenes that were the carbon, the hydrogen, the nitrogen, the sulfur, and the oxygen, and 2 more atoms for the air that were the oxygen and the nitrogen. So to discretize if the reaction mechanisms undergoes by the effect of the nitrogen or the oxygen, we have to consider 5 atoms different for the asphaltene and two more atoms for the air, right? So when the distance between the asphaltene and the oxygen atom present in the oxygen air environment are in no close, we can say that breaking of this bond is associated precisely to the oxidation effect and not to the pyrolysis. So that was the idea that we use to create the reaction pathway for the asphaltene oxidation at the pressure evaluated, right? And according to the other question, I synthesized almost 50 nanocatalysts. Yes, I synthesized carbon materials, carbon zero gel, carbon nanospheres, lanthanides based on Syrian nanoparticles, metal oxides, combinations between the carbon materials with the lanthanides and the metal oxides, with the lanthanides and the metal oxides. And based on all that analysis, I created one catalyst in particular that is a Syria-based nanocatalyst with a cubic morphology. This catalyst has the advantage that when we are controlling the morphology of itself, allows to expose more reactive planes like the 1-1-1 facet planes in the surface, which is highly reactive and allows the conversion of the asphaltenes into lighter hydrocarbons and even into hydrogen. So also when we doped this cubic Syrian nanoparticle or nanocatalyst with a mass fraction of 1% of nickel, and palladium, we maximize the conversion of the asphaltene and the production of hydrogen and light hydrocarbons during that oxidation. And this catalyst presents a lot of benefits, like the reduction of the decomposition temperature of the heavier fractions from around 400 degrees Celsius to less than 200 degrees Celsius. And as I said, the production of more valuable products like the hydrogen and light hydrocarbons, and the self-regeneration capacity, which is also associated with the redox cycles. Yes, as we know, the Syria can transform the Syria 4 ions into Syria 3 ions during an oxidative atmosphere, and it allows the self-regeneration during the decomposition of the heavier fractions. So the half-life of this nanocatalyst is very good, and the industrial application of this material is with total security will be really good in terms of the economic. And also we are working with the biggest oil Colombia company in the pilot and injection of this nanocatalyst in our oil Colombian field. So I expected that the pilot will be done in the middle of the next year. Thank you so much.
Any further questions from our judges?
So Oscar, thank you for a very interesting paper. I guess and it's a very good study that you have made in trying to understand the reaction mechanisms. But looking in the lab, actually, you have not conducted any core experiments yet to know how this combustion front moves within the core, and when you subsequently go to the feed, your combustion front is going to move from producing well to injection well to producing well. The issue is going to be that the temperatures are going to continue to change along that front, and also to some degree, the pressure will change along the front. How much control do you think you can have on this process?
Sorry, could you repeat the question, please?
Okay, the question is that the experiments that the lab experiments you've done are good, but if you do the experiments in a core, a long core, 2 feet or 3 feet long core, where the combustion front is moving, right? Your temperatures are going to change along the front. You have several different fronts, and the temperature is going to change in each one of those. And also the pressure is going to change. So in actual field process, how much control do you think you will be able to have?
Okay, thank you for your question. Up to this point, the pressure variation during same experimental test has not been done. We have evaluated for a constant pressure and how the reactivity of the molecules changes by hitting the molecules from 100 to 600. But up to this point, we have not made some variation of the pressure during this analysis. And I hope to make that during the next work. So I really thankful for your appreciation and your comment.
Thank you, Oscar.
Thank you.
Thank you. So that concludes the question and answer session for Oscar. So we will now move on to the next presentation. Thank you, Oscar.
Thank you.
So we will now move on to Mahmoud Shakiba, winner of the Southwestern North America Paper Contest.
Hello everyone, my name is Mahmoud Shakiba and today I'm going to present the results of my research work on multi-scale spatial characterization of fractures and pattern reconstruction using Ripley's K-function. Let me start off with asking this question. Why do we care about fractures in the subsurface? The answer is pretty clear. Fractures are everywhere and they have a strong impact on every aspect of oil and gas operation. Basically, fractures can be either our friend or foe. For example, in hydraulic fracturing of unconventional wells, fractures help us produce the hydrocarbon trapped in low permeability rock. Or similarly, in naturally fractured reservoirs, they significantly increase the productivity of the wells. On the other hand, fractures can also be a major reason for concern. For example, in water, gas, or chemical flooding, fractures can provide a high permeability channel that connects injectors to producers, resulting in early breakthrough. Or for example, during drilling, fractures can cause lost circulation, which may result in significant drilling failure. So in general, identification and characterization of fractures is really a critical topic in oil and gas operations. Fractures can be directly measured in 1 dimension or 2 dimension. In 1D, there are several approaches. The first one is by using scan lines as shown in this picture. Scan lines are long tapes that you can put on outcrops to measure the spacing between fractures. Another method is through borehole image logs, where we can see fractures as sinusoids. And lastly, we can also use core samples to see the location of the fractures. To visualize fracture measurements in 1D, we can use stick plots as shown at the bottom. The stick plot displays the location of the fractures along the study interval. We can also perform fracture measurements in 2D by tracking fractures either on outcrops or by using satellite images. We can use these two methods to capture fracture trace maps as shown at the bottom. So the goal of this work is to use the data that we measure in 1 dimension or 2 dimension to study the spatial characteristics of the fractures in the subsurface. But the challenge is that the spatial characterization of fractures can be a very complicated task. First of all, it's hard to sample fractures directly in the subsurface. Depending on the orientation of the fractures and orientation of the wells, the number of fractures that a well intersects might be quite different from one case to another. Another challenge is that fractures often exhibit multi-scale characteristics. For example, if you look at the distribution of fracture spacings, fracture length, or aperture size, often you see that they span across multiple length scales. And lastly, some of the statistical measures that we often use to model fractures, such as histograms, are not good enough to capture the spatial arrangement of fractures. For example, you may think that if two fracture sets have the exact same spacing histograms in 1D, they're essentially similar. But it turns out this is not true. For example, these two fracture sets, set 1 and set 2, have the exact same histogram for fracture spacing, shown on the left-hand side. But they show different patterns. For example, in set 1, fractures are distributed more or less random along the study interval, while in set 2 there is a fracture cluster in the middle. Same limitations exist in 2D as well. For example, in these two fracture networks, set 1 and set 2, they have identical histograms for fracture length shown at the top and fracture orientation, but they show different degrees of spatial connectivity. In these two pictures, the intersection between fractures are shown with red dots. If you look at set 1, you can see that the connectivity is very limited. There are only a few intersections between fractures, while in set 2, fractures are connected over the entire study domain, although they have the same histograms for fracture length and orientation. So the message here is that we cannot fully capture the spatial arrangement of fractures by only looking at conventional statistical measures such as histograms. So the main research goal here is to introduce more sophisticated statistical methods to characterize spatial distribution of fractures. We would like to know whether a fracture arrangement is random, clustered, or anti-clustered, and if they change as a function of length scale. And then I will use our new method to introduce a new algorithm based on a pattern reconstruction to generate new fracture network realizations. Okay, the statistical method that I have used in this work is called Ripley's K-function. Ripley's K-function is a method of point pattern analysis that primarily applies to the distribution of discrete points in the space. We can use Ripley's K-function to characterize a spatial organization. Ripley's K-function is calculated as the expected number of points that fall within a search area of radius h from any randomly selected point inside the study domain. If this number of neighbors is greater than what we expect from a random distribution, then we call the pattern clustered. If the number of neighbors is less, then we call the spatial pattern anti-clustered. So there is always a comparison made with random distributions to identify what type of spatial arrangements we have for our data points. The 1D and 2D formulations of the K-functions are shown here. The 1D formulation, the first line, applies to fracture measurements from scan lines, borehole image logs, or subsurface core samples. The 2D formulation applies to fracture networks in 2D. Before we can use these two equations, we have to convert or transform our fracture network to point patterns. To do that, instead of considering fracture traces, we evaluate the fracture midpoints, fracture intersection points, or fracture tips. Now that we have a network of points, we can use these equations for spatial characterization. So the way that the calculation works, for example in 2D, is that we put a search window of radius h, let's say 1 meter, on top of one of the points, and then we count the number of neighbors that fall inside the circle. Then we move this window over to another point and we count the number of neighbors. We continue this until all the points inside the study domain are visited. Then we take the average of all the calculations to find k sub n at 1 meter length scale. If kn is greater than 1, then our pattern would be clustered. If it is less than 1, then our pattern would be anti-clustered. So this would be the spatial arrangement at 1 meter. We can change the size of the circle and repeat the calculation to find the spatial arrangement at another length scale. To illustrate the application of the K-function, I present two examples of natural fracture datasets. The first example is a 1D fracture dataset originally published in the work of Merritt et al. In 2018. I've also been to the field myself and I've performed some additional measurements for validation and quality control. The fracture measurements are performed using a scan line of approximately 59 meters long on a limestone outcrop in Pedernales Falls State Park in Texas. There are 916 fractures, and here is the stick plot showing the location of the fractures along the scan line. As you see, most of the fractures are concentrated on the left-hand side of the scan line, which can be also observed from the intensity plot at the bottom. The second example is a two-dimensional fracture dataset measured by satellite imagery from a limestone outcrop in the Oman Mountains from Zib et al. In 2013. The map of fracture traces and the histograms of fracture length and orientations are shown here. Although, as you can see in the trace maps, although fractures are scattered over the entire study domain, there are not that many intersections between them. So the connectivity is pretty limited in this specific fracture network. Here are the results of the K-function analysis for the 1D dataset in PET-analysis. On the x-axis, we have length scale, and on the y-axis, we have normalized K-function. The horizontal line that goes through 1 is for a random fracture pattern, and the shaded region around it is the 95% confidence limit. The red line is the normalized K-function for the PET-analysis. As you see, the K-function for PET-analysis is always greater than 1, indicating a persistent multi-scale clustering arrangement. The red line is above the confidence limit at length scales larger than 3 times 10 to the power of minus 3 meter here, and which means that they're statistically significant. Now, if the fracture arrangement were random, as shown on the right-hand side, then the normalized K-function would have completely fallen inside the confidence interval. So basically, using the K-function, we can distinguish a clustered fracture pattern, like the PET-analysis, from a random fracture pattern. For the two-dimensional fracture dataset in Oman, the K-function analysis for a subset of fracture midpoints is shown here. As you see, at length scales less than 9 meter here, the K-function is less than 1 and the fractures are anti-clustered. While at larger length scales, the fractures form a random arrangement. This is different that we saw in PET-analysis. We can do the same analysis for the full dataset as well, as shown on the right-hand side. For example, this figure shows that for fracture intersection points, shown at the top, the spatial arrangement is clustered across all the length scale. So K-function provides a tool to identify different fracture arrangements at different length scales. Now, in the second half of the presentation, I will introduce a method for fracture pattern reconstruction based on Ripley's K-function. In various petroleum engineering applications, we may want to create fracture model realizations in 1 dimension or in 2 dimension that are similar to the fractures that we observe or we measure in the field. For example, we may want to run uncertainty analysis, or we may want to evaluate different production scenarios. For such applications, it's important that the fracture realizations that we generate honor the properties and the spatial patterns of the original fracture networks. To do so, here I propose a simulation technique based on pattern reconstruction algorithm, which is formulated as a non-parametric optimization problem with a loss function. The flowchart is shown on the right-hand side. The simulation starts with an arbitrary fracture arrangement. Then in each iteration, we randomly perturb the location of fractures, and we accept the new arrangement only if it reduces the loss function between the candidate realization and the observed dataset. The main advantage of this simulation technique is that it can incorporate any complex spatial pattern as long as they can be quantified in a loss function. For the 1D application, the loss function is the L2 norm of the error in the K-function over various length scale. We use K-function to match the characteristics of the point pattern in the space. For the 2D application, the variograms of fracture length and the variograms of the fracture strike angle are also included into the loss function to capture the variation of fracture attributes over the study domain. Let me first show you the results of the pattern reconstruction for the 1D dataset in PET-analysis. On the left, we have the fracture patterns shown by stick plots. The top row is the PET-analysis itself, which I tried to simulate. The second row here is the initial guess, and then the rest of the lines are fracture realizations after various iterations. For example, after 100, 1,000, 10,000, and 100,000. On the right, we compare the statistical properties of the fracture realizations with PET-analysis. PET-analysis is shown in red and the simulation results are in blue. The column on the left is the histogram of fracture spacing. In the middle, we have the parallel distribution of fracture spacing, and on the right is the K-function calculation. As you see, the mismatch between peri-analysis and the candidate realization decreases as the number of iterations increases. Finally, after 100,000 iterations, we get a very close match between our realizations and the peri-analysis. And also, if you look at the scan line after 100,000 iterations, we can see that we have zones of clustering separated by zones of anti-clustering in the middle, similar to the observation in peri-analysis. I also applied the pattern reconstruction algorithm to the Z two-dimensional fracture dataset. This figure demonstrates the map views of the original fracture network, the initial random fracture network, and the final simulated fracture network after 100,000 iterations using our algorithm. Remember that the loss function in 2D includes the K function, the variogram of fracture length, and the variogram of the fracture strike angle. So for each one of these parameters inside the loss function, the figures are shown on the right-hand side. I've plotted these functions for isotropy case, which is the first row, for the 45-degree azimuth in the second row, and the 135-degree azimuth in the last row. As you can see in these figures, the final simulated pattern, which is shown with blue lines, is very close to the original fracture network in Z data, which is shown with red lines. However, the random fracture network, shown with green lines, exhibit different spatial characteristics, although it has the same fracture traces. Also, if you look at the fracture intersection points, shown by red dots, you can see that the number of fracture intersections in the random network is much higher than the other two. So the network is basically more connected compared to the original network and compared to the simulated network. This example clearly indicates that if two fracture networks has the same distribution of fracture length and orientations, they are not necessarily similar. To further investigate that, I use numerical flow simulations to compare flow behavior of the original fracture network with the random network and with the simulated fracture network. The complex geometries of fractures are integrated into the reservoir simulation model using a method called Embedded Discrete Fracture Model, or EDFM. EDFM provides a computationally efficient algorithm for modeling complex fracture geometries using a structured reservoir grid. The created discrete fracture models are shown here at the bottom. The reservoir size is 200 meter by 200 meter by 45 meter in X, Y, and Z directions, and the domain is discretized into 100 grid blocks in both X and Y directions. There is an injection well on the lower right corner of the model, injecting water at the rate of 300 bbl per day. A production well is defined on the upper left corner with bottom hole pressure of 1000 psi. Initially, reservoir pressure is 3000 psi and oil and water saturations are 0.8 and 0.2 respectively. Here are the results of flow simulations. The water saturation maps after 540 days of injections are shown here at the bottom. We can see that the simulated fracture network generated by a pattern reconstruction algorithm, shown on the right-hand side, has a similar water flooding sweep efficiency compared to the original network shown on the left-hand side. In both cases, the water front is still far away from the production well. However, if you look at the random fracture network in the middle, you can see that the sweep efficiency is highly non-uniform and the water has already reached a production well. The random fracture network has the same exact fracture traces, but it has different spatial characteristics than the other two fracture networks, because the number of fracture intersections is higher and therefore the degree of network connectivity is larger. Also, if we look at the water production rates on the right-hand side, we can see that the breakthrough time in the original and the simulated fracture network occur approximately at the same time, while in the random fracture network, water breaks through 220 days earlier. So the point here is that the random distribution of fractures cannot really capture the spatial patterns. Instead, the fracture realization that we generated by our simulation algorithm has the same spatial and also the flow characteristics as the original fracture network. So to summarize, conventional methods that only use fracture histograms cannot capture the spatial characteristics of fractures. Two fracture networks that have the exact same histograms can be quite different. As a solution to this problem, I introduced a spatial data analytics method based on Ripley's K-function to characterize fracture arrangements into clustered, anti-clustered, or random. Also, using K-function, I proposed a pattern reconstruction algorithm to generate fracture realizations that are not only similar in terms of spatial characteristics, but also honor the flow behavior of the original fracture network. These methods can be simply applied to other subsurface applications that deal with fracture prediction. With that, I finished the presentation. Thank you very much for your time and attention. I would be happy to answer your questions.
Thank you. We now open the floor up for judges for any questions.
Hello, Mahmoud. Thank you for
Hello.
your insightful presentation. Very good research. And yeah, as I'm actually working on unconventional, so fracture characterization is definitely a very challenging topic now. But your work definitely provides some insights and advanced this topic. My question is that I saw your research is still limited to 2D. Is it easy or possible to extend this to 3D, taking the deep angle into account?
Yeah, definitely, because deep angle is another geometric parameter that you can define into the simulation. But the challenge in terms of going from 2D to 3D, it's not because of the algorithm, it's because of like the measurement techniques. Because if you look at like the literature, most of the techniques that people use, out in the field to capture or to study fractures are limited to 1D or 2D. There are like some limited, three-dimensional techniques that you can, see what is the deep angle of the fractures deep into the formation, but they are not well, developed yet. So if there are like data available, definitely, because for the simulation algorithm, deep angle is just another parameter that you can introduce. But in terms of the validation, are there data sets that you can validate it against after you run the simulation?
Yes, great answer. Thank you.
Thank you.
Any further questions from the judges?
Yes. So this is Mahmoud. Thank you very much for a very interesting study that you're doing. I was looking at your simulation study, and the fracture network that you have taken, in a way, is in the direction from injection well to producing well. I was wondering if you had a fracture network which was more transverse between injection well to production well, the results could be quite different.
Of course, yeah, definitely. So I selected the direction of producer and injection well, specifically in the direction of the fractures to show some of like the extreme, cases that you can run into. So if you haven't, predicted, that, there are like fractures in the formation that is like aligned with your injection production wells, then so for example, in that specific case, the water showed up in the production well 200 days earlier. But as you mentioned, if I rotate the direction of the injector and producer 290 degrees, then the difference wouldn't be much because most of the fracture would be perpendicular to the direction of the water flow. So you shouldn't see that much difference. So that's also another parameter that you need to consider in terms of like well placement or water flood optimization, definitely.
And in fact, just most of the time when we'll go into a fluid injection project, we'll try to find out if there is a natural fracture system. And we'll try to locate injection wells in such a way that we can minimize the effect of fractures.
Exactly, yeah.
So in fact, you can use simulation to do the same, to actually find out in terms of determining the location of those wells, so long as you know your fracture distributions.
Yeah, so as I said, so you cannot just pick like fracture network and just randomly distribute it into your simulation model, because you would be surprised by the results that you get and compared to the reality. So definitely there should be a measurement, done first in terms of, looking at the outcrops, looking at, image logs, and then proceed with the next step of, field development, whether it could be, drilling an injection well or, EOR or other, processes that you may choose. So the message here is that, do the measurement, and then after you do the measurement, use like sound statistical methods to generate your reservoir simulations.
Yeah, good observation. Absolutely.
Thank you.
Any further questions from the judges?
Just a quick question. Have you had a chance to apply it to any real reservoirs?
To any actual reservoir?
Yeah.
So I tried to look up, some papers in the literature. The problem is that there are some naturally fractured reservoirs that they have production data, but they don't, they didn't publish like the data on fracture measurements. But on the other hand, there are some papers with measurements on fractures, but they didn't, publish production. Yeah, so I haven't been able to find, a paper that includes both.
Okay.
So yeah, definitely that would be an option, something that we have to check against, in case if you have all the data, then why not? Yeah.
Yeah. Okay. Yeah, those are the challenges that you have in the university.
Yeah.
Okay, thank you, Mahmood. So that concludes our Q&A session for Mahmood's presentation. Thank you so much for your presentation. We now move on to Muhammad Ali Ahmadi, who won the Canada Regional Paper Contest.
Hello everyone, this is Mohammed Ali Ahmadi. I'm doing my PhD at the University of Calgary. It's my honor to be here at the International SP Contest 2021 and present my research to you as an expert of oil industry. Today I'm going to talk about the phase behavior modeling of surfactant and cement heavy oil systems using microdynamic simulation. For today's presentation, at first, I'm going to give you a brief introductory about my research, and then I will jump into the methodology that I've used. And after that, I will talk about the results that I've gained so far and discuss more about them. And then I will give you the conclusions based on those results, and finally the references that I've used for this presentation. My research is all about development of digital oil based on the molecular structure of oil and perform MD simulation to extract different thermodynamic parameters, for example, interfacial tension, interaction energies, or viscosity, or stuff like that, and then put them into the reservoir simulation model to see what's really happening in the reservoir scale and what's going to happen there. And the cool thing about this workflow and the MD simulation is we are able to formulate a wide range of additives from surfactants, polymers, solvents, non-condensable gas. And this workflow, it's not limited to heavy oil and bitumen. And you can do it in a conventional oil and unconventional as well, like shale oil and shale gas. And with the aim of this workflow, we end up getting an optimized additive formulation, which means that we are in a position to get higher and higher oil production. So as I mentioned before, I've used MD simulation, and I'm just trying to break it down as simple as possible for you. What the MD does is actually applying the Newton law in a molecular scale. And what Newton's law tells us is the amount of force, the gradient of potential, is equal to the mass of the molecule times to the acceleration of that specific molecule. And to capture all of those potential energies to find the forces, we have to have series of equations like this that we call it force field. And if you can see inside these equations, you see several parameters that what we call it force field parameters. I'm not going to go through each of those equations and parameters, but if you are really interested in to get more details about force field and corresponding parameters, I really encourage you to take a look at our published review paper in a very prestigious journal in Advances in Colloid and Interface Science. So in our case, I've used the compass force field, which is very well accepted and validated for the surfactants and hydrocarbon as well. And for example, if with the aim of force field, you are able to capture, for example, the bond stretching between these atoms, or the non-bond potential between these atoms, or the angle bending between these bonds, or the torsion of this bond as well, and something like that. And for doing MD simulation, we have to follow the well-accepted workflow that you can see here. It comprises 4 different steps. The first step is initialization step. In this step, we have to select our chemical structure, then the force field and force field parameters. And based on the thermodynamic condition we have, in my case, I wanted to see what's going on in a in situ thermal process. So I've used pressure of 5 megapascal and temperature of 498 Kelvin. That's a typical value for the steam assisted gravity energy here in Canada. And then we have to optimize the geometry to get the minimum energy of a system, and after that we have to equilibrate the system at the given pressure and temperature. And finally, that's the production stage. We have to perform the MD simulation to extract the trajectories and analyze them for calculating the properties that we want to have. And for constructing and generating the heavy oil sample, I've used 2 different resins. The only difference between these 2 resins is the presence of this sulfur heteroatom, and actually I've used these 2 because I wanted to see the effect of this sulfur atom if we, for example, we have sulfur inside the resin. And also 2 different types of asphaltene, the archipelago asphaltene and the island asphaltene, for the sake of comparison, and figure out the effect of type of asphaltene on an output. And C46H50S as an aromatic and C20H42 as saturate. And for a surfactant phase, I've used 2 different anionic surfactants, sodium dodecyl benzene sulfonate SDBS and sodium dodecyl sulfate here. And as you can see, the only difference between these 2 anionic surfactants is the connector between the polar head and the hydrophobic tail. And I've used this configuration because I want to see the interfacial behavior between the steam phase with and without surfactant and the heavy oil at that given pressure and temperature. And I've used exactly the same workflow that I've explained before, and in this table you see the system identification for different type of asphaltene and resin and surfactants here. So one of the informative parameters that MT provides us is the radial distribution function RDF. The RDF is defined as a ratio of a density at different distance from a specific molecule to the overall bulk density of the inside the system. So in this case, keep that in mind. For bitumen and heavy oil, the high viscosity comes from the asphaltene stacking inside the system. So I decided to plot RDF for a pair of asphaltene molecules. The left plot is for island asphaltene, the right one is for archipelago. And what actually RDF tells us is if we've seen spikes at a specific distance, it means that we have a macromolecular or cluster structure at that specific distance. Take a look at this RDF plot. As you can see, at the distance of almost 5 angstrom, we've seen several spikes there. In other words, at the distance of 5 angstrom, based on the visualization, we've seen the cluster of asphaltene molecules. So, in other words, if we can reduce this spike, it means that we are in a position to having lower viscosity. So by adding the sodium dodecyl benzene sulfonate SDBS to the system, as you can see the blue line, the amount of that spark, significantly decreased, and it means that we are in a position that having lower viscosity in the presence of the surfactant. The same story is here for the archipelago asphaltene. And also I decided to plot the RDF for a pair of asphaltene and surfactant molecule. And as you can see, for a low range distance lower than 2 angstrom, we've seen several spikes here, which means that based on the visualization, we have hydrogen bond network between the polar head of surfactant and polar part of asphaltene. The left one is for island asphaltene and the right one is for archipelago asphaltene. Another useful parameter that we can get from MD is self-diffusion coefficient. I decided to use self-diffusion coefficient of water molecules inside the system to validate our simulation job. And for doing this, at first I have to measure and plot the mean square displacement of water molecules, and based on this equation and based on the autocorrelation function, we end up with this equation for calculating the self-diffusion coefficient of water molecules inside the system. The top right plot is for the system with island asphaltene, the bottom one is for archipelago. And as you can see, if you take a look at this plot, you can see the self-diffusion coefficient of water at this temperature is very close to the experimental value that reported in the literature. And it means that in terms of self-diffusion coefficient of water, our simulation job is validated. And another thermodynamic parameter that's really helpful for us is interaction energy between the bitumen and the steam phase. And in this case, based on the interaction energy, we can find out what's really happened inside the system. And as you can see, the total interaction energy, the top one is for island, for system with island asphaltene, and the bottom one is the total interaction energy inside system with archipelago asphaltenes. So the higher interaction energy between the steam and bitumen phase means that we are in a position to get lower interfacial tension and probably lower viscosity inside the system. And in a larger scale, it means that we are most likely to get higher oil production in such a system. So another good thing about the interaction energy, actually, with the aim of interaction energy, we are able to see if we are testing different type of additives. With the aim of interaction energy, we are able to decide which one interacts better inside the system and which one doesn't. And also, based on the contribution of van der Waals and Kolov interaction inside the system, we can decide how we can optimize the additive. For example, in our case, as you can see, the contribution of van der Waals interaction energy is much higher than column interaction inside the system. What does that mean actually? It means that in a system, we have to take a look at the hydrophobic part of our additive, in this case, our surfactants. And as you can see, the van der Waals interaction for systems with sodium dodecyl benzene sulfonate are higher than system with sodium dodecyl sulfate. And it means that the hydrophobic part inside the surfactant, inside the chemical formula of the surfactant, in this case the benzene ring inside the SDBS, plays an important role in the van der Waals interaction. In other words, if we want to optimize our surfactant, we have to work on the benzene connector in terms of the position of the connector or the number of connectors that we can add to the surfactant to improve and optimize the surfactant structure. And another important point is based on the total interaction energy inside the system, those systems with SDBS actually has a higher interaction energy compared to other systems with and without surfactants. And it means that we are in a position to get lower interfacial tension, lower viscosity, and probably higher ore production. And one of the interesting interfacial properties is interfacial thickness. And for doing that, we have to use these two arrow functions here to determine the density profile of both steam and bitumen phases, and with the aim of those density profiles we are able to calculate the interfacial thickness between the steam and bitumen. And as you can see, adding surfactant to the system could really increase the interfacial thickness between the steam and bitumen. And another point that I would like to highlight is for systems with island asphaltene, the resin with sulfur actually have a negative side effect. But on the other hand, for systems with archipelago, actually we couldn't see any meaningful effect of sulfur heteroatom inside the resin structure. And another thing about the interfacial thickness is the higher the interfacial thickness means that the lower interfacial tension we get. So if we can improve, if we can increase the interfacial thickness, it means that we are able to reduce the viscosity, reduce the interfacial tension, and probably higher oil production. And the last parameter is interfacial tension between the steam and bitumen phase. And based on this integral equation, we can calculate the interfacial tension. And because we've used the visual equation for the pressure, we end up with this simple equation for calculating the interfacial tension. And for example, consider the system with island asphaltene and the resin without sulfur, and with the SDBS surfactant, we can get the interfacial tension around 10 millinewton per meter. But for exactly the same system, but without the surfactant, as you can see, we got the interfacial tension around 30-31 millinewton per meter. Another point that I would like to assert on it is because I didn't have the experimental data for validating the interfacial tension results, I decided to perform exactly the same workflow of MD simulation on a reference molecule dodecaine at the constant pressure and different temperature, and compare the outputs of the MD simulation to experimental data published in the literature to validate my simulation job. And as you can see, the MD output for the interfacial tension between the water and dodecaine at different temperature is very close to the experimental data reported in the Zepieri and colleagues in 2001. And it means that in terms of interfacial tension, again, our simulation job is validated. So as conclusions, as we explained throughout this presentation, the structure of asphaltene, surfactant, and resin inside the system could significantly affect the phase behavior and interaction between different phases. For example, the benzene ring on the surfactant on STBS could improve the van der Waals interaction between the surfactant and polar part of heavy oil, and also, for example, the sulfur heteroatom inside the resin structure could significantly decrease the interaction between the sodium dodecyl sulfate and asphaltene, and adding surfactant could really improve the interaction energy between steam and bitumen. And among all those systems, the system with STBS has the highest interaction energy. And having said that, the contribution of van der Waals interactions was much higher than Coulomb interactions for all systems. And in terms of interfacial properties, adding surfactant could improve the interfacial thickness between heavy oil droplet and a steam phase, and also reduce drastically the interfacial tension between these two phases as well. And the effect of sulfur heteroatom inside the resin structure on interfacial thickness, as I've explained, in system with island, it has a negative side effect, but inside the system with archipelago asphaltenes doesn't have meaningful effect. And here's the references that I've used for this presentation. I would like to take a moment to thank all of my sponsors who support my work during my PhD journey, especially the Government of Canada by Vanier Scholarship, and the Killam Trust, Alberta Innovates, SP, and Energy Simulation for partial funding for my research. And also thank you all for taking time and attend this virtual presentation. And I'll be glad to take your questions if you have any.
Thank you. And we would now like to invite the judges to ask any questions.
Hi, Muhammad Ali.
Hi, how are you doing?
Fine, thank you. Very great presentation. Thank you. Thank you so much for the explanations. So I'm looking at your slide 14, where you did the comparison between the IFTs that you measured and the IFT from data in literature. And you mentioned that it's quite close. So I'm a bit curious as to what is the error we would expect in the IFTs that prompted you to say that these results are quite close.
That the error I almost 5 to 6%. The error about the MD simulation compared to those results is almost 5 to 6%. But I have to mention that because I've used the simple point charge water, I would highly recommend to, because based on the limitation on the page, I couldn't add lots of information there. I have to cut them all. But I would highly recommend to use other type of waters, TIP3, TIP4, and make average from those to to close the gap. 5%, that would be enough. For engineers, always that's okay. 5%, that's okay. But in terms of scientific work, if you want to close the gap below the 5%, you should make some average between different systems, simple point charge or TIP3 or TIP5 or stuff like that.
All right, thank you.
You're welcome.
Any further questions from our judges? Okay, so with that long pause, I will take that as no further question for Muhammad Ali. Oh, okay, Anil, go ahead.
Yeah, I have a question. I'll go ahead. I want to thank you, Muhammad Ali, for a very interesting discussion and presentation.
You're very welcome.
Can you help us understand what are the actual, crude oil systems that you used? I guess being in Alberta, you probably use some of the actual crude oil, heavy oil systems for your computations.
That's in terms of the real molecular structure, you mean?
Yeah.
At the Athabasca.
Okay, so all this work has to do with Athabasca.
Yeah.
Okay.
But as I explained in the presentation, it's not limited to Athabasca. You can do it for every reservoir you have, every type of oil and gas you have.
Right. Yeah, this is a very interesting application to apply surfactants to for the heavy oil systems.
Because that's the first time ever we've used, and I've used this one for heavy oil, bitumen, and oil sand.
So what kind of efficiencies you might expect with the surfactant system versus the non-surfactant system?
Oh, that's a great question, because in the next couple of weeks, you will hear something in the media about that, because we end up getting a very promising result in terms of reducing the steam oil ratio, because that's the one of the suffers for heavy oil and bitumen production is a steam to oil ratio. And if we can reduce the steam to oil ratio, it means that we end up having lower greenhouse gas emission and lower the water usage. And at the same time, if we can improve the oil recovery, we are reduce the break-even point in terms of the oil price. So in the pessimistic condition, we could reduce 20%. We could reduce 20% of steam oil ratio and improve 5% of oil recovery. But in an optimistic condition, because we performed a wide range of different conditions, and in optimistic condition, we could end up having 40% reduction in steam to oil ratio and 12% of oil production increase.
Well, that will be a very different, that will be a very distinctive and significant result.
Yeah.
So, yeah, so that's a part of another study.
Yeah, because let me tell you, I didn't submit anything to the SP, as you may notice that I didn't, and I didn't request to publish this work right now, because we are in a mid of patenting this stuff, and we, in terms of different things, and because I'm collaborating with the oil producers here in Canada, in terms of some oil production and oil production companies, they have some policies, about the publishing data and stuff like that. I had to take care of those things in when I decided to submit this paper to SPE contest.
Thank you, Muhammad Ali. Appreciate your
You're welcome.
work.
Okay, so that concludes our Q&A session for Muhammad Ali's presentation. Thank you so much for your presentation, Muhammad Ali.
Very much, I appreciate it. Have a good one.
Thank you so much. You too. So now we would like to move on. We'll now move on to the next presentation. We now have Timothy Anderson, who won the Western North America paper contest.
Hello everyone, my name is Tim Anderson from Stanford University. Today I'll be presenting on reconstruction and synthesis of source rock images at the pore scale. This is an outline of what I'll be covering in this presentation. I'll start off by giving an introduction to shale imaging, scale translation, and image-based characterization of shale source rocks, and describe the characterization and image reconstruction workflow we present in this work. From here, I'll go over two applications of this workflow. First, I'll discuss 2D microscopy image enhancement and the extension of this methodology to 3D volume reconstruction and flow simulation in the reconstructed image volumes. The second application is a novel porous media image volume synthesis algorithm specialized for synthesis of shale image volumes. I'll wrap up with some conclusions and discuss future steps in these lines of work. Shale gas resources are critical for the global energy supply. For example, since 2009, shale gas has made up the majority of the increase in U.S. domestic energy production. Shales are highly multi-scale source rocks, so everything from nanoscale up to macroscale features are important to understand for recovery in shale formations. Image-based characterization, particularly nano-image-based characterization, combined with digital rock physics techniques, are critical for the study of shale source rocks. And while digital rock physics in conjunction with image-based characterization represents a very powerful toolbox, there are some central problems that arise when applying these techniques to shales. First and foremost, acquisition of nano images for shales tends to be very expensive, time-consuming, and/or sample-destructive. Secondly, nanoscale shale images are often acquired in 2D, for example with electron microscopy techniques, but we need 3D information to fully characterize a sample. And finally, partly as a consequence of the first challenge, the third challenge is that the data we acquire tends to be too scarce to accurately estimate the petrophysical properties. The data sets are simply too small to do this estimation properly. So, what we propose in this work is to address these challenges by applying deep learning generative models to shale source rock imaging. A central theme of this work is reconstructing 3D volumes when we only have 2D training data available. So shales exhibit features over 10 or more orders of magnitude, and consequently scale translation techniques are incredibly important for understanding and characterizing shale reservoirs. Scale translation we define most broadly as predicting or connecting information in physics across length scales. Image-based scale translation is one part of scale translation and can be a very important avenue towards scale translation. We can acquire multimodal or multi-scale images, use digital rock physics to compute properties from single image modalities at a single scale, and then use the images themselves to link the information across length scales. We link images to the physics, and the images provide the link across length scales. In the figure below, we show rock properties ranging from nanoporosity up to faults in gray, and then different imaging techniques for these different length scales in blue. There are four main processes we lump together under this umbrella of image-based scale translation. First, we have upscaling, where we have fine grid data and we like to derive an optimal upscale representation of that data. Secondly, we have downscaling, where we have coarse grid data and we want to predict the fine scale data, or more often, we would like to predict a distribution of realizations for the fine grid data. In addition to these two more traditional scale translation techniques, we also include data generation, where we have a single or multimodality data set at a single length scale, for example, focus ion beam milled scanning electron microscopy, and we would like to create synthetic images of that same data set. And finally, we have data translation, where we have multiple modalities acquired at the same length scale, and we like to move in between these modalities. So these four processes allow us to traverse this entire data space across modalities and length scales. In this work, we're going to primarily focus on data translation techniques and data generation. The image-based characterization workflow we use in this work is shown here. We start off with image acquisition of the sample. This provides the reconstructed image coming off the machine. From there, we can curate, pre-process, and subsample the images to put the data into a suitable form for machine learning model training. While this is shown as a sequential process, in reality there is an iterative process here where the data pre-processing pipeline you choose needs to work in tandem with the type of model you're using and the type of results you want from that model. Once your machine learning model is trained, though, you can then move on to image generation or image prediction, post-processing of the images, including filtering or segmentation into a simulation domain, and finally morphological and petrophysical analysis of the reconstructed volume. Our contributions in this work are shown here. In data translation, we apply image-to-image neural networks to predict destructive shale nanoscale microscopy images from non-destructive input data. We develop a novel regularization method to reconstruct volumes when we only have 2D training data available, and we simulate flow through the reconstructed image volumes. For data synthesis, we propose and implement a new porous media synthesis algorithm, which is the first such algorithm to be able to generate 3D grayscale volumes from only 2D training data. We apply this algorithm to generate sandstone micro-CT volumes and shale multimodal nanoscale image volumes. So the first area we'll look at is image data modality translation. Multimodal and multiscale imaging is an emerging area for shale characterization, and our work here seeks to combine two existing lines of work. First, we have work on making predictions from coarse-scale rock images using machine learning models, and the second area is multimodal imaging. Multimodal imaging is common in the medical imaging community, but there's been no prior work applying these techniques to shale characterization. Our goal here is we want to address this trade-off that arises between microscopy imaging modalities for shales using such machine learning techniques. Shale imaging modalities are split primarily into destructive imaging techniques, which offer high resolution and high contrast images but destroy the sample during acquisition. On the other side, we have non-destructive imaging techniques that preserve the sample for further experimentation, but often offer lower resolution or contrast. What we want to do is assimilate multimodal imaging so we can have the best of both worlds. We can have non-destructive imaging that preserves the sample, as well as enhance the resolution and contrast to be more similar to that of the destructive imaging modalities. To study this, we use a dual modality image dataset acquired for a Vaca Muerta shale sample shown here. After preliminary imaging, the original core is milled down to a 600 micron diameter core with a 30 micron diameter plug protruding. The 30 micron plug is imaged using a transmission X-ray microscope to obtain the reconstructed image volume with the plug shown at the far left. This plug is then milled down and imaged using focused ion beam scanning electron microscopy using the setup shown in the center right. In this setup, we image each successive slice using a scanning electron microscope, then mill down the sample a bit using a focused ion beam. We do this iteratively, which allows us to obtain SEM image slices throughout the entire image volume, such as the one shown at the far right here. If we look at the resolution for these images, they both have similar XY resolution, but the FibSum images have variable Z direction resolution, so we have to align this data into paired image data that's suitable for the image translation models. And this is one of the big challenges in multimodal imaging. Our image prediction models require paired training data, but as a consequence of the imaging modalities, it's difficult to have good paired data. First and foremost, if we're trying to align XY image slices, automated registration algorithms based on mutual information or pyramid methods will often break down because the imaging modalities are so different. And secondly, the FibSum images, for example, have variable thickness in the Z direction, so we need to match them to the corresponding TXM slice or correct for things such as tilting factors that arise during the acquisition process. This is the only way we can get a successful match for the corresponding TXM image slice that provides us with a suitable data set. And overall, the data alignment issue is one of the biggest challenges in multimodal imaging, resolving these differences in the image acquisition environment. But once we do have a well-aligned data set, we can then move on to the machine learning models themselves. The task we want to address with these machine learning models is we want to predict a FibSum image from an input TXM image slice. This problem has elements of both image translation and single image super resolution, so we turn to the baseline models associated with each of these tasks. Feed-forward convolutional neural networks, the PIX-to-PIX conditional generative adversarial network model for image translation, and the super resolution GAN model, which is the baseline for single image super resolution. In all of these models, we feed our TXM image into a resonant generator, such as the one shown at the right here, and get a predicted SEM image. In the feed-forward CNN model, the predicted SEM image is then fed into an image similarity loss to train the generator network. The PIX-to-PIX and SR-GAN models are similar, but tack on a secondary discriminator neural network and a GAN loss term. The addition of the generative adversarial network loss and discriminator network allows the generator network to learn to create more realistic-looking images. So these are the results for the 2D to 2D image prediction. The quantitative metrics we use include peak signal-to-noise ratio, which measures the total error between the predicted and ground truth images, the structural similarity index metric, which measures the difference in spatial statistics between the two images, and the structural texture similarity index metric, which is a modification of SSIM and is meant to measure perceptual similarity. We find that the feed-forward CNN model is the best for reconstructing the low-density regions in the rock. This is important because the low-density regions are assumed to contain the kerogen and low-density minerals where the flow takes place. So if we do want to simulate and visualize flow through the volume, it's important to reconstruct the darker regions shown here. In terms of the quantitative metrics, we find that the PIX-to-PIX model does the best for PSNR and SSIM, and the SR-GAN model does the best for perceptual similarity. So while these 2D to 2D models are very powerful, what we need in the end is to reconstruct 3D volumes. Unfortunately, using traditional models, the 3D to 3D prediction problem typically requires 3D training data. However, as we've discussed, when doing multimodal shell imaging, usually one or more of the modalities will only be acquired in 2D. So our proposed solution to this problem is to add a regularization term to training 2D to 2D models to improve our slice-wise reconstruction of the 3D volume. We use this assumption that shell image volumes have sparse Z gradients as we move in between fib-sum slices in the Z direction. So we can enforce continuity in the Z direction by including a Jacobian penalty term in the training. This is the PIX-to-PIX model, similar to the SR-GAN model, but with a continuity loss term tacked on with a green arrow here. This continuity loss will enforce continuity as we're moving between successive TXM image slices and improve continuity in the rock features as we move between predicted fib-sum slices. So these are the results for a 3D volume prediction using this regularization. During training, we train the same way as with the 2D to 2D models, but with this added regularization term. During evaluation, we independently pass the XY image slices through the 2D to 2D network and concatenate in the Z direction to create the volume shown here. In the middle, we have the baseline volume that includes no regularization, and on the right, we have the predicted fib-sum volume with the regularization. What we see on this rock face here is that we have significantly improved continuity in the rock features as we're moving in the Z direction when we include this regularization term. This result shows that regularizing the 2D to 2D models with the Z continuity prior, we can reconstruct 3D information even when we only have 2D training data available. So finally, to close the loop on this, we simulate flow through the segmented lower density regions of the generated volume. On the left, we have an example simulation domain where we've segmented the low density regions, including the kerogen and lower density minerals. In the middle, we have the pressure field resulting from simulating a pressure gradient over the volume using the PerGeo software package, and on the right, we have streamlined visualization of flow through the segmented volume. For the permeability, we find that the permeability for both the original and the regularized model tends to be on the order of tens of microdarcies, which is higher than that we would expect for shell at the matrix scale, likely due to some of the assumptions we make while segmenting the simulation domain. However, the more important takeaway here is that the streamlined visualization shows that using image translation techniques, we are able to visualize flow in the volume using completely non-destructive image data. This is a capability we did not have without application of these image translation models, showing how the image translation has improved our ability to characterize shales. So, moving on to image data synthesis, nanoscale imaging data often suffers from data scarcity, so we're unable to estimate properties from the limited data we have. The main idea for this part of the work is we want to train a generative model to synthesize images of the sample, and then we can estimate morphological or petrophysical properties of the sample by evaluating them for synthetic images sampled from this generative model. Methods for porous media image synthesis are divided between two main camps. On the one side, we have statistical methods which seek to recreate spatial statistics of the training data, and on the other side, we have deep learning-based methods which use models similar to those discussed in the previous section on image translation. While these methods have shown a lot of success for a pretty wide range of rock types, there are some limitations when we want to apply these to shales. First, we want to do 3D grayscale generation from 2D images because in shales, the grayscale values contain information about the mineralogy of the sample. However, existing methods for 3D generation from 2D images are limited to binary image data. If we're doing 3D grayscale generation, we need to use deep learning-based methods that require 3D training data. And finally, multimodal and multiscale image generation remains completely unexplored in this area. So to address these challenges, we turn to an entirely different type of deep generative model known as generative flow models, or GLOW models. In a GLOW model, we model our data points x as a function of a Gaussian random vector z, and we train an invertible mapping g theta between our data space and our latent vector z. During training, we maximize the likelihood function of the observed data points, and then during evaluation, we can sample these z's from the known distribution and feed them through the reverse network to obtain our sampled data points x. Generative flow models have several desirable properties. First is the tractable likelihood function that has applications to maximum likelihood estimation problems, such as those arising in image reconstruction problems. It also has a latent space projection property, which has potential applications to image modality translation. And finally, and most importantly for our purposes, it has the latent space interpolation property, which is the property that we use to generate 3D image sequences. For this work, we introduced what we call the rock flow algorithm. It uses the latent space interpolation property of the generative flow model to build up these porous media image volumes. The latent space interpolation property states that linear interpolation in the latent space will give a semantic interpolation or connection in the image space. So we can build up a 3D volume of porous media by sampling independent ZI vectors, which we call anchor slice vectors, taking a linear combination of these ZIs in the latent space, and then transforming these into the image space to create a connected image volume such as the one shown here. By doing this, we can build up image volumes such as the one shown in the video at the right. This is an image volume for a Bentheimer sandstone sample. By only training on 2D images and using this latent space interpolation property, as shown in the video, we're able to successfully build up image volumes of porous media. The slide shows on the left the same video from the previous slide, and in the middle, we have a video traversing the same image volume but in the XZ plane. What we see is that images in the XZ plane, which are orthogonal to the image generation plane, the one on the left, these XZ plane images resemble the Bentheimer sandstone image, except for what we term this jittering effect on the pore grain phase boundary. However, as we see from the video on the right, if we apply a simple spherical meeting filter, we can actually mitigate quite a bit of this jittering effect and remove this artifact. Furthermore, we can also show that these generated volumes will match based on morphological and petrophysical properties of interest. This result shows that the latent space interpolation property combined with 2D data allows us to create rock volumes that match not only visually based on what we'd expect for the training data, but also match based on the morphological petrophysical properties that we're interested in. And finally, one of the big advantages of our approach is the ability to extend to grayscale, and specifically grayscale multimodal image volume generation. Here we train on the same multimodal image data set used in the image translation work, and we generate the multimodal image data by treating each image modality as a separate image channel in the network. Doing this, we can actually build up image volumes such as the one seen here when the data itself only exists in 2D. We see that in both the orthogonal planes as well as the image generation plane, the XY plane. The images do look like realistic FibSem and TXM images. So even when the data itself is only two-dimensional data, the Rockflow algorithm is able to successfully generate image volumes. So in conclusion, we've shown that deep generative models enable new directions in shell characterization methods. We're able to use these models to overcome some of the limitations of the imaging machines to create image volumes, and we're able to address data scarcity by generating realistic new data samples. These advances are important because improved nanoscale characterization for shales has direct implications for production from shale formations due to the multiscale nature of shale source rocks. On the data translation side, we've shown that regularization during training creates volumes suitable for flow simulation, and on the data synthesis side, we've shown accurate recreation of 3D volumes and the ability to generate multimodal and grayscale volumes when we only have 2D data. As far as next steps in this work, we would like to integrate unpaired image data into training the data translation models. This would allow us to take advantage of the huge amount of single modality image data that exists for shale samples. We also want to quantify uncertainty in the rock properties using the synthetic shale image data. Related work has done this for a Bentheimer sandstone sample, but we would like to extend this analysis to shale samples. And then longer term, we would like to build up multi-scale image volumes taking nanoporosity obtained from ones of nanometer imaging techniques such as tunnel electron microscopy and impose that nanoporosity for shales into the tens or hundreds of nanometer resolution simulation domains that we've obtained from our image translation process. In doing so, we can build up multi-scale image volumes and obtain more accurate calculations for the petrophysical and morphological properties that we're interested in. So here are my acknowledgments. I'd like to thank my advisor, Professor Anthony Komsek from Stanford University, as well as my lab mates and collaborators whose input has been extremely helpful on this project. And finally, our funding sources. Code for these projects are available on our lab's GitHub pages. Here are my references. So thank you all for listening today, and I'd be happy to take any questions during the live session.
Thank you, Timothy. We would now like to invite the judges to ask any questions.
I can go first. Thank you, Timothy, for your nice presentation. Very insightful work. And my question is, what's the dimension of your model? So it is practical to apply it to like a large scale reservoir simulation.
Yeah, so are you talking about the image sizes or like the field of view of the images?
Oh, yes.
Yeah, so the images that I showed there were 128 voxels in each direction, and the resolution was about 33 nanometers per voxel. So you have what is that? About 2 micron resolution in each direction. So that's the field of view. However, the way the architectures are made, you could extend that. You could extend that field of view in the XY direction. You could extend that field of view indefinitely because you can just kind of take your network and run it over the entire image. So if we wanted to do a full nano CT volume, then you could just run your architecture over the entire volume. In the Z direction, because we don't, because all of the Z direction information is actually enforced in the model, it's not, it's enforced through the training, not in the actual architecture of the model. You have no limitation in the Z direction. So even though the ones that I showed had 128 voxels in the Z direction, you could actually extend that indefinitely because there's no, for both the image synthesis and the image translation models, because there's no, the Z direction isn't actually encoded in the model the Z direction is not actually encoded when you're evaluating the model, it's encoded in the model training. Does that make sense?
Oh, yes, that answers my question. Thank you.
Okay.
Any further questions? Okay, go ahead, Daniel.
Yeah. Okay. So Timothy, thank you very much for a very interesting discussion here. What is your starting point for generating 2D images? What kind of samples do you start out with?
You just need, so we explored this for the Vaca Muerta shell sample that I showed. We also had another, we had a FibSum data set for a different shell sample, and then the Bentheimer sandstone sample was kind of our baseline. So those were the ones that we looked at. You don't have any really big limitations on the sample other than you have this assumption that the sample is at least somewhat isotropic in the rock features. So if I take an image slice from any image plane, it will roughly look the same. That assumption is only going to hold up on the matrix scale, but if you're within roughly say you're like pore chord length scale for your rock image, then that assumption should hold up pretty well. But that's the only really firm assumption that you have. Now, if your sample did have like really strong bedding, for example, as you're going in between image slices, then that would be unsuitable for the image generation method. Now, the image translation method, your sample really just needs to have the Z continuity that we assume. That's the only really strong assumption. So these models are pretty well generalized. As long as you stay kind of at the grain scale or the matrix scale.
So how do you actually validate your 3D model that you come up with?
So for the image synthesis models, those we can compute the petrophysical properties and the Minkowski functionals, and then compare those to the ground truth data. So when we do that for the Bentheimer sandstone sample, we find that we have a pretty good match based on the morphological and the petrophysical properties. Validation of the image translation models is quite a bit more difficult because we inherently do not have 3D information for that data set. So in the paper that we put out on this project, what we actually do is we segment the images, evaluate Minkowski functionals for the segmentations, and then compare the Minkowski functionals in the XY, XZ, and YZ directions to the Minkowski functionals computed for the test data set. Because the idea is that at least the statistical distribution of those functionals should be the same in all three image planes, because we're assuming that the rock is relatively isotropic. It should be relatively the same in those image planes as to the test data set.
So in a new area or a given reservoir, how many samples do you need, to come up with
we were able to train these on only about 150 full slice images.
because we subsample those images into 128 blocks. So you end up with, we use 10,000 subsampled images. The actual number of unique images, I believe, is a bit lower than that. But what you can do is you can take these very large field of view, high resolution images in your scanning electron microscope, and then you subsample the smaller image patches. This is also why the images I showed are trained on 128 by 128 2D images, because that was the image size that we found gave us a good enough field of view to actually learn the rock features, but also when we were subsampling the full slices, gave us enough training data to successfully train the models. So if we're talking about a reservoir, if we wanted to characterize a reservoir rock, you would probably need in the couple hundreds range of FibSim images if you wanted to apply these models to a new data set.
Right. So for a given shale reservoir, I think they can provide you probably some kind of sidewall course or something that you can then do your SEM and TEM. So how many samples do you need to kind of characterize?
This is done all off one sample.
This is all off one sample, right?
Yeah, this is done from one sample. So if this were to actually get deployed to production, you would need you would need data from each core that was distinctly different from the other cores. So if you have a lot of heterogeneity in the reservoir, then that might get a bit more difficult. But the samples that we've shown, all the models that we've shown here were trained off data sets acquired from a single core.
Right. So how would you go about integrating? Let's say you had several core samples, and you just worked on one data sample, and then you worked on a second data sample and third sample. How would you then integrate all these 3D simulations that you would come up with?
If we had multiple samples, the training would remain the same. We would just kind of mix the samples together as we're training the models. And you would actually probably likely end up with a much more generalized model, because you're not just training the same sample data over and over. You're training across a lot more rock features, and that's kind of related to the point that I made about future work on the last slide, where we want to the kind of long-term goal for this work is going to be to integrate unpaired image data from lots of different samples into training these models. Because one of the issues that we kind of ran into more as a consequence of the data that we had is that it's not totally clear how the models are going to generalize when we're looking at lots of different samples, or say, for example, if we're training on a Bentheimer and a Berea sandstone, would these be able to work equally well if we're training off different shales or different sandstones at the same time? So.
Right. Okay. Thank you. Thanks, Timothy. Yeah, very interesting work.
Oh, thank you.
Hey, Timothy, very nice work. I have just one question. So you mentioned for the 2D to 2D image prediction, you used SSIM and PSNR. So do you also use any physics-based, like say petrophysical properties, to kind of evaluate how well you're doing?
For the image translation models, we do not, because we don't have ground truth data. We just kind of have the best we can do for the petrophysical properties is see if we're in the ballpark for the image translation models, because we don't have the ground truth 3D data for that sample. Our multimodal data set was only 2D. So for the for the image translation models, no, we don't have ground truth data for the petrophysical properties. We just have kind of estimates. For the image synthesis models, however, at least for the Bentheimer sandstone sample, we do. So kind of a sister project to my work that I presented here actually applied the algorithm I showed to the Bentheimer sandstone samples and did more in-depth analysis on the petrophysical properties. And that one, using both an LBM solver and a Navier-Stokes solver, showed that you obtain pretty good matches for a porosity permeability curve for the Bentheimer sandstone sample. So the petrophysical properties matched for the Bentheimer sandstone sample. That was the one that we could actually do ground truth analysis, because the Bentheimer sandstone, we have a 3D micro CT volume for that, so we can actually compute those figures. Yeah, I'd be that paper is actually just got accepted and published like 2 weeks ago. So I'd be happy to forward it to you if you'd like. So.
Hi team, great presentation. I have one question. So you used a deep learning based generative model for the porous media image synthesis. And I'm wondering how other models would have performed in a similar situation. If there was any basis for comparing with the existing methods. And if you could just throw some light on what the existing methods are. Thank you.
Yes, yeah. So for the existing methods, as I mentioned, there's two kind of main families of those. One are the statistical methods. So what those try to do is actually you can think they almost kind of take like different particles in the rock and then optimize to decide if they're supposed to be a 1 or a 0. And they optimize all the different voxels to try to mimic the spatial statistics of the 2D training data. Or just the training data in general. So and those mostly focus on methods for binary image generation, because they're mostly looking at, is it a 1 or a 0, and then slowly iteratively flipping between 1s and 0s until you're matching the spatial statistics in each direction. So those are the statistical methods. Those are a little older and were pioneered. Actually, Martin Blunt's group did a lot of the kind of foundational work on those. So those are a bit older. The newer methods are based on different deep learning methods. So, we presented a GLOW model, a generative flow model. The more popular one is a generative adversarial network. So the network the kind of model that we showed for the image translation, that's a very similar deep learning architecture as they use for most of the baseline image generation, image synthesis models as well. So we actually did that comparison for the Kedon limestone and Berea sandstone baseline data sets. One of the kind of first papers in deep learning image synthesis for porous media used a generative adversarial network. So we applied our model to the Berea and the Kedon data sets and then compared it to their results. What we found is that their method did a bit better in terms of the mean curvature Minkowski functional. And that's because their model doesn't suffer as much from that sort of jittering effect on the pore grain phase boundary that we pointed out. That jittering effect is likely because of kind of continuity issues as you're doing this reversal of the network. So there are ways that we could probably we could adapt our training for that in the future, but we kind of left that for future work. So that's one of the advantages of the deep learning based method is you maybe don't have as many artifacts. The downside is that the deep learning based method has to have 3D data. So arguably when you have your full 3D ground truth data, either single or multimodality, then the deep learning model definitely has some advantages and the results do look a bit better. But when you're limited to the 2D training data, then you have to resort to something like our model because the deep learning models, the existing ones out there don't seem to be able to handle that sort of data. So.
All right, thank you very much.
Yeah.
Any further questions from our judges? Okay, so with that silence, I will assume that no further questions from our judges. So thank you, Timothy, for your presentation and Q&A session.
Thank you.
So thank you all very much. So this now brings us to the end of the presentation for today's contest. A big thank you to all of you who are involved. We will be signing off now, during which time the judges will now reveal and rank their scores. I would like to ask all judges to stay online for a few more minutes and we will move to a breakout room. But before we go, don't forget we will be announcing the winners of all the SPE divisions during the Student Award ceremony on Thursday. If you haven't registered to attend this yet, you can find all the details at the ATCE webpage, which you can find at atce.org, along with more information on all our events. Thank you again, everyone, and we hope you have a great ATCE. Okay, just our judges on just online, so we don't need to move into a breakout.
Fantastic.